Very good. Hello, everybody. Thank you for joining us today for AIAA Los Angeles, Las Vegas section event. Let me see. Do you see? Okay, very good. This is, honestly speaking, the first attempt to bring the gravity-dependent science technology technical committee, formerly microgravity space process technical committee, with the LA section. Although the LA section did a couple of times with other technical committee, including space architecture, has been quite successful. Initially from 30, 40 people, it grew up more than 200 attendees. So this is the first time, so bear with us. And I personally apologize. We wish we could do it in a very nice hotel, but because we kind of, you'll see what I'm trying to say is that we actually put most of our funding in this one major event, annual awards dinner. That's actually I was talking to Adrian, about the possibility for certain awards. So each year we did awards. We put most of the resources in a nice hotel, and then we just have the student branch mini-conference in the same room, and you can see this is very nice library. We thank so much. Longtail Library, we have the nice audio-visual remote online meeting board, as you can see here. Very comfortable location. So really appreciate. But hopefully next time we can reserve hotel or something like that, or restaurant. But just a few words about AIAA Los Angeles section. As you know, AIAA is the #1 leading aerospace organization, started from Wright Brothers and Robert Goddard, almost 100-year history, merged from two distinguished organizations into AIAA in 1963. So since it's a joint event, so I kind of tell this is first. Folks online, can you see the charts? Can you see the chart, Bob?
Yes, we can.
Very good, thank you. Oh, hi, Jacob. Yeah, I'll move you to panelists shortly. So this is, so LA section has a very long history and used to be covered everywhere in this area. We have, now we have the very nice weekly newsletter with professional artists designing this. You can see F-22 flying and many other nice cover. So awards dinner this year is going to be May 14. In Cambria Hotel LAX, we're going to recognize the president of Aerospace Corporation, being the honorary fellow this year at AIAA, Mr. Steve Izakowicz. Then we also have a fellow, Dr. Binay Goyal. Then you can see this is a picture from last year. Then we have our former section chair, Dr. Jeff Bushell, and the new current section chair, Luis Cueva, our technical chair, Mr. Gary Moore. Actually, he designed the Apollo capsule landing module, the injector. So we are, it's very exciting. He retired from TRW. And at the bottom, you can see Dr. James Worth. In case you didn't know, actually, he has a company called Microgravity. There's a lot of history with SpaceX, and you can see give the students scholarship to a very outstanding student. So AIAA LA section has been very active. The reason why I mentioned, I want to get everybody interested in AIAA and participate. Oh, sorry. So we just have the event same here in the same room. 3 weeks ago, we have a tour Impulse Space, and then we have our CEO, Mr. Craig Murray, and Lindsay Mitchell from headquarters join us. And locally, you can see there are so many aerospace companies. There's a legacy from the legendary North American X-15 and Apollo mission to shuttle they're all made here. Then your Gitai, Vast Space, Boeing, then of course we have Varda and Aerospace Lab just moved in recently, and many joined us. JPL, Jet Zero, you name it, Rocket Lab Aerospace Corporation. I don't want to miss anyone. Northrop, SpaceX, and more. So this is a very exciting area. So I really try to get everybody interested. Then we also have casual happy hour, unfortunately happy hour. We also have astronomy night. You can see the 7 planet parade. And April 26th, we have Mr. Adamo. I think Joe just mentioned about if we go to Mars, and it's going to be dominated by orbital mechanics. So this is an event talking about a proposal to put a depot, astrodynamic design to put a depot in between Earth and Mars. Then we have the planetary sun-shaped program, Dr. Bradley and Jeff are going to talk about the exciting proposal. Then we actually also have event recognized local student, professional. This is USC student Rocket Lab. They just, in case you didn't realize, their student rocket just broke the world record of international amateur altitude record. So they are not just a student rocket. This is in USC. It's very exciting. And we also visit, San Bernardino, a local school, and help them to find their career. So as you can see, this building a big family with the local. So we need the industry help. We also academia. And this is, I'm trying to tell you some of the important people at AIAA, Dr. Jeff Rochelle, Miss Mary Lee Wheaton in the AIAA Awards Committee. And this is Distinguished Professor of USC, Professor Azad Mahdi. So we have a lot of good people here. So coming back to the gravitational technology, then formerly this committee was called Microgravity and Space Process, but because the industry is moving to different various direction of the gravity-dependent technology. By the way, actually it has never been really microgravity. This is 10⁻⁶, so we actually changed the name. So I don't want to take more time, but this is a very important thing. Is in December, NASA just announced a new LEO microgravity strategy, which they link Moon and Mars. You can see in the background with the Moon and the red dot Mars to link the existing 20, 30 years of experience ISS microgravity task. Okay, so this is Pam Melroy, Colonel Pam Melroy, talking about it. Of course, now it's a new administration, and we have Miss Jim Free in SciTech also emphasize this initiative from NASA. And we are trying to, the technical committee, GDST or MSPTC, we are trying to engage the community from industry. You can see that many player in the LEO or other, gravity situation. And in case you didn't know, actually Varda has termed it called hypo and hypergravity situation. It's very exciting, and also academia and many wonderful universities, including material, propulsion, combustion, magnetohydrodynamics, and biomedicine. So we have featured the Aerospace America Year in Review in Microgravity. This includes Professor Rob Furrows, the Blue Origin NS-26 Pride, and our Vice Chair Alvaro is a professor in Georgia Tech, and put this nicely in our annual review. So we try to, we need your help, and if you would like to join us, we'll still have a spot in the committee as well. And if you're local, you're welcome to participate at the LA section activity. So we also have national webinar for the technical committee. So Dr. Jason Lee gave a talk for Mars analog. Very exciting. We're looking for the next speaker. Maybe the Anthony from Catalonia online here, he will be the next, but you are welcome if you are interested. Then we also have award. Is a great opportunity. In addition to the LA section Technical Excellence Award I mentioned earlier, that's the local section. This is a National Microgravity Award. So if you and your company interested, we have announced it, so we are in the nomination process. So AIAA has SciTech and Ascend. Our technical committee is heavily involved in both of them. And this is SciTech, and our new CEO, Mr. Craig Murray. He used to, I think he's still with Vast Space. So you can see Dr. Daniel Hastings, and we have technical committee board, and we have Arda Happy Hour with a group of Arda. Marat is here. So it's very interesting. We try to connect to everyone and have each. With technical committee, we also meet and can see these are the international and the experts, then online in person talking about microgravity related aspect. And we have presentation in SciTech. This is Dr. Moultrie from UCSD. This is Nina from ASU from Spacebox. They actually got the new lab invested in Arizona State University. So there are many great things happen. And in fact, actually recently I just realized in Florida, Central Florida University, there is a lab called the Stephen Hawking Microgravity Laboratory. So it's kind of very interesting. And biomedical, reproduction, making baby in space, microgravity situation. This is fluid control, propellant control. Then you can see very nice discussion. Seizure, they have a biomedical device, very nicely tracked, automated. There's Alvaro and his student, and you can see we have panel. So I wish you can join us to enjoy this wonderful activity. So we also have white paper. So if you're interested in doing some kind of industry, say standard or kind of report review, we can work with you together. Even you are not a member, we can work with you in a called a working group, those kind of things. So we're working on a new journal on this wonderful technical committee. I'm going to move you to the next speaker, but before that, for the in-person attendees, if you want to have coffee, coffee in the kitchen. We have you donut and cupcake, so please enjoy them. So for the speakers, we prepared a lunchbox for them, but for other attendees, hey Kevin, Jen, nice to meet you. We have a corner burger, right? 30-second walking. You're welcome to, because there's no lunch break. So if you want to go to the restroom, please wave hand. It's right here outside the door, but please wave hand to the librarian. So thank you very much. So we are going to welcome the next speaker, the first speaker of the day, Adrian. He's going to talk about the exciting project he was working on with BARDA space industry. In case you didn't know, they actually just have a IM-2 capsule landed in Australia March 3rd, right? March 3rd. And it's hypersonic reentry, Mark 25th and above. They actually achieved it last year. And I just read it, M3 is ready, right?
It's up.
It's up, you see? It's so fast. He's going to tell you a lot of exciting story, and I'm going to put up his chart. Okay, thank you so much. Place a pointer. Okay, and this is back. This is the neck chart. I'm going to put your chart on.
Sounds good. And should I stand right here?
Or no, you can stand anywhere. Okay.
Thank you so much for having me here. It's a pleasure. I'm so excited that it's local as well. This is one exit away from the exit I usually take to head over to BARDA, and there's so much that has been accomplished over the past couple of years, so it's great to get to know some of you, and it's exciting to tell you a little bit about what we're working at BARDA. Thank you again, Ken, for organizing and having me here. So this is a view from W1 on the way back to Earth. If you check out the BARDA YouTube channel, you can watch the full thing, but it was just, I know a lot of the people here have been working with satellites in aerospace for a long time, so you might be a little bit more used to these images. I come from the material science, process development side, so every time I see something like this, it just blows my mind. So this was a GoPro camera looking out on the journey back. There were crystals inside. For today's talk, I'm going to focus on how does gravity help with particle engineering. I'll talk a little bit about mission 1, but come find me if you have more questions. The focus here is going to be how we're trying to untangle the role of gravity in controlling particle size distribution. All set?
Yeah, does it work?
Yep.
Okay.
And a lot of the work I'll present was done by Kanjar Kapel. I'm very fortunate to work with an amazing team. His background is in chemical engineering and process development. So what BARDA has built is really the first commercial orbital pharmaceutical processing capability that's completely independent of space stations. So we can launch on a rideshare, do what we need to do in space, and then come back, people on board. The whole idea is to try to make access to space affordable, easy, fast. As Ken mentioned, W2 recently returned. W3 just went up last night. We'll be launching a couple more this year. And over time, we're going to aim to get to once a month and then even more than that. And that's what really helps take this idea of microgravity processing from research to something that can be applied across industries. BARDA's focus is on the pharmaceutical sector. So here's the microgravity lab. Just want to highlight it because a lot of this talk is going to focus on what we're doing just a couple miles away. So we get to space with Falcon 9. We're up in orbit. We'll do our materials processing. Then when we come back, it's certainly hypersonic reentry, and the temperature on the surface of the craft gets very high. But on the inside, we have great thermal control. So for the first mission, we held 5 degrees C all the way to touchdown. It took about 2 hours to reach room temperature as we equilibrated with the ambient environment. And during that 8 months, people always have questions of, if you make something in space, is it going to survive? What are you going to have when it comes back? And so what we set out to do with the first mission is investigate that question. We're also interested to find out, would you get a different crystal structure if you made the crystal in space? We ended up growing a metastable form, the least stable crystalline form of a drug called ritonavir, and we crystallized it in space. We brought it back, and it came back as that same form. And on board, we also had controls. So we had amorphous ritonavir, which is very prone to crystallization. It stayed amorphous. We had form 1, form 2 as well. There were no changes to the control samples. And when we looked at the chemical purity, they matched the chemical purity of samples that were in a fridge here on Earth throughout that extended mission duration. And so what we're able to demonstrate is the ability to safely bring back what we make in space, even if it is a metastable crystal form. And can get into the history of ritonavir, but knowing what crystal structure you have and being able to control it is critical for the safety of pharmaceuticals. This talk is going to focus on how we're trying to really apply microgravity to enabling better pharmaceuticals. It's very much focused on reactor uniformity and mixing, how gravity plays a role, and what advantage you could get from microgravity. For the audience here, it will hopefully give you some insights as to what pharmaceutical industry tries to achieve. And then for those in the pharma industry, a lot of this content helps understand why to think about gravity. It's not something pharmaceutical scientists or chemical engineers think about in the same way that aerospace engineers do, but it can play a pretty significant role. So the work I'm going to talk about is published. If you want all the details, it's in the Journal of Crystal Growth and Design. So all the data and detailed description, the methods and everything will be there. And the motivation for why we're doing this is a lot of the reason many of the people are online and in this room is that the space industry is transforming very rapidly. It used to be that space was something for governments. Now it's also something for commercial entities. And a lot of that has been driven by the advancements in space infrastructure, whether it's lower cost satellite platforms, lower cost launch. It's now possible to do things in an economically viable way, in a way you couldn't 20, 30 years ago. So we're just at that threshold now where this idea of making something in space with better properties is starting to become economically viable. So we can not just do science about how could things be better in microgravity, but we can start to apply that idea to make better products for use here on Earth. And one of the really interesting things is if you think about what people do in microgravity, what they try to achieve, and how industry works today, they're not necessarily aligned. If you look at a lot of the publications, the focus, especially for crystallization, is quiescent environments. So try to hold everything still, very gentle, low energy, let the crystals grow. And one of the most prominent applications has been for growing larger crystals that are more uniform for structural determination to solve the crystal structure. But that's not all crystallization is for. A lot of pharmaceuticals are crystalline for stability, for shelf life, for storage, and the properties of those crystals can change the dosing and the bioavailability. So if you look at how crystals are made, it's often not quiescent. They're stirred, they're agitated, which is very different from how microgravity research is done. So now there's this challenge of how do we adapt what's known about microgravity to industry use cases, and what is the underlying physics and chemistry of these systems so that we can figure out when do you use microgravity, when do you not, why does it matter? And just a little bit about crystallization. So a crystal is an ordered lattice. It can be atoms or molecules. I lost the screen there. But when you put molecules in a solution, they're dissolved. They're not necessarily in contact with each other. If you want to make a crystal, you increase the concentration until there's enough driving force to bring the crystals together. Once you get to a certain concentration, there's not enough solvent molecules to go around, and it starts to become favorable to form solids together with the molecules that are in solution. As you keep increasing the concentration, you start to get precipitation or crystallization. And the first step is usually nucleation. Nucleation is when the crystals first start to appear, and then there's growth of those nuclei, and then you end up with your ordered crystals. The question is often, okay, well, why does gravity matter? How's it going to make a change? And if you talk to a chemist, they'll be very surprised, because whenever you look at how atoms bond and molecules interact, there's no gravity term in those equations. You're looking at electrostatic interactions that are much, much stronger than, it's not that the gravity between the two molecules is holding them together. Welcome back. Okay, so that was crystallization. You're looking at charge. That's what's holding things together. There's not a gravity term, so why would microgravity or hypergravity, why would there be a difference? There's three aspects that we look at BARDA right now. We're looking at concentration gradients, sedimentation, and convection. That last piece, convection, is talked about a lot in the microgravity literature. It's especially important for the quiescent crystallization. When you have a crystal that's growing here on Earth, you do have convection. The reason for that is because of density differences in the fluid. As you consume solute, you end up with less molecules in the region around the base of the crystal. It's lower density. It will rise, and you get those convective plumes. Turns out that those plumes drive transport of molecules to the growing crystal surface, so it does impact the results. And in microgravity, if you can suppress that convection, you can get very uniform crystals, and that is an advantage. But that's not the only thing that gravity does. Some of the things are actually, very, very, people know about this gravity effect all the time. Sedimentation. The crystal is often denser than the media. It can also be less dense than the media. So it often falls to the bottom of the container. Here on Earth, we stir and we agitate, and that's how we manage sedimentation. But there's also concentration gradients. If you're growing your crystal, you're driving a concentration change, and if your mixing system is not fast enough versus the rate of growth of the crystals, you have pockets of low density, high density, and they'll stratify in your reactor depending how it's set up. All of these issues get worse on scale-up. So when you do something in a 1 microliter drop, the distance the molecule has to travel to get to a crystal is so small that the diffusion Brownian motion is good enough. When you go and start to think about manufacturing something, and you're at tens of liters, hundreds of liters, these mixing problems become big headaches. So while the chemists will say, why should I think about gravity? When Palin, one of the things he said is, gravity is my mortal enemy. I deal with gravity all the time, and I know how I'm going to apply your technology to get to better process results. I'm not able to advance. If I could. Next one. Oh, thank you. So just a little more of the technical detail before we start to get to the data. So I mentioned the way crystals grow. You have nucleation, then there's growth. There's more taxonomy in there, and it will be helpful to talk through a few of these to put the upcoming work in context. The way we often think about crystallization is you increase the concentration, you get to a certain point, the crystals start to grow. That will be primary nucleation and growth. For one way you can think about it is in terms of if it's a temperature-driven process, we're changing the concentration not by adding more molecules, but what we're doing instead is we're changing the solubility of the system. So as things cool down, the solubility limit changes, and so the relative concentration versus that solubility limit is the knob that we're using. So for the experiments I'm going to talk about, they were all cooling crystallizations. So that's why the x-axis is temperature, and the y-axis, you can think about that as the concentration. So as you start the cooling crystallization, once you get to a certain threshold, crystals start to spontaneously form. That's primary nucleation. And once they start growing, they start consuming the molecules in the system. So then the concentration in solution drops. Because it's spontaneous, if you want to make a drug that's safe, that's a problem. Not every crystal is going to look the same. It might be a case that you're getting crystallization on impurities that are present at locations in the container that are cold spots. It's not well controlled. If you have a distribution of crystal sizes, you're not going to have a consistent dose. You might even have different crystal forms. To get around that problem, what the pharmaceutical industry often does is use seeds to start. So you skip over the nucleation step. You have some very well-controlled starting materials. Those are the seed crystals. You place them in the reactor, then you use your temperature knob to grow the crystals. And that helps you get very well-controlled crystals. But sometimes there's something surprising that can happen called secondary nucleation. So even though you're running a seeded crystallization, there's still the potential for nucleation processes to take place. And for the system we looked at, L-histidine, turns out that even though you're below the threshold for spontaneous nucleation, the seed crystals act almost like a catalyst for driving nucleation of small crystals on the surfaces of the seeds. So for the paper here and the details, it will be a secondary nucleation-driven process. That's something we had to untangle for the system.
Is that something that often might be contamination dependent? Is trace amounts of something else?
Yep, that's a great question. So Joe asked, is this something that's sensitive to contamination? Absolutely. All of these nucleation and crystal growth processes can be very sensitive to impurities. So like for the example of ritonavir, when it first came to market, they only knew about one crystal form. Once they scaled up and got to a very robust manufacturing process, eventually they improved the purity of their starting precursors, and all of a sudden a new crystal form appeared, and they had an impurity that was stabilizing a metastable form, and that's the only form they knew about. And it was only when they got the impurities out that the other crystal form became around. So absolutely, keeping everything clean is critical. So the way we figure out how these crystals grow, we start in the lab. We don't have to figure everything out in space. So we have reaction calorimeters with probes that we can insert into the volume. So we have video microscopy. We can watch the crystals grow in real time. We have laser instruments that measure the particle size. We have Raman spectrometers, infrared spectrometers, and we're able to watch the concentration over time, the crystal form over time, and we could track how that process is evolving, and that lets us figure out, do we have a primary nucleation event, secondary nucleation? That's how we untangle the mechanisms. And we could also ask questions about what is the threshold for nucleation to take place. So the cartoon that I showed, you can turn that into, you can collect the data version of that and create those maps for those systems. We spent a lot of time in the lab doing that, and then we start to ask, okay, how is the system going to change as we vary gravity? So we also have reactors on a large diameter centrifuge. It's about 2 meters in diameter. We use some commercial off-the-shelf reactors like the Crystal 16. We have custom reactors that we've built that can support a large range of different crystallization processes. And we'll vary the rotation rate to vary the effective gravity. And that lets us start to probe, how does that system navigate that process diagram as you start to vary gravity? So here is L-histidine. It's a molecule that we used for understanding crystallization. It's well studied across academia and the industry. It has different polymorphic outcomes. There was a parabolic flight where L-histidine was crystallized, and they found some potential changes in the form that is made in a microgravity environment. So we set out to study how would that system behave at various gravity levels. This was a seeded cooling crystallization. So we prepare the L-histidine, we warm it up to ensure that everything is fully dissolved. Then we cool it down to start to supersaturate, so we're inside that metastable zone width where crystallization and growth can take place. And then there's a controlled cooling profile once the seeds are added that drives the growth. So the whole process takes a few hours. And we did everything on still a relatively small scale. I mentioned a lot of these effects are size dependent. This was in about 1.5 milliliters of fluid in an HPLC bottle. And we were stirring. So that's the other big change. It's not a quiescent crystallization. We're agitating the system fairly aggressively. So these charts here help with understanding what crystallization happens just at 1G, with not on the centrifuge. So the y-axis is the concentration, the x-axis is the temperature, the blue line is the solubility curve determined experimentally. The green dashed line is the threshold for primary nucleation, which is also determined experimentally. And then we track how the concentration of the fluid changes once we add the seeds. So the seeds are added, and then we're able to monitor the concentration over time. Because we're inside of the metastable zone width, we don't expect to see nucleation. However, when we look at the particle size, we see something different. So the other plot is showing the counts, how many particles, and the x-axis is the size. So how many particles of which size. The peak labeled primary, those are the seed crystals. If we're doing a seeded crystallization, you would expect that that peak should shift to the right, the primary particles should get bigger. That's not what we saw. What we saw was the appearance of the second peak that got larger, and that's the evidence for secondary nucleation driving the crystallization process for L-histidine. And it is not what we expected because we're inside the metastable zone width, and the mechanism for it is secondary nucleation. To confirm that's what's going on, we use the video microscopy. So here are some images of the crystals. The large particles are the primary seeds that we add. And then I have a green circle, those are the secondary particles that form. So there's nucleation on the faces of the seeds. Those small crystals break off during the agitation. And that's the source for that secondary peak that grows over time for the crystallization. So that's how we've been able to determine that for L-histidine cooling crystallization, it's governed by secondary nucleation. And then we wanted to figure out what will happen as a function of gravity. So we ran the crystallization at various G levels. Here I'm showing 1G, 2G, 3G, 4G, 5G. And then we measured the particle size by laser diffraction. We saw shifts in the particle size distribution depending on the gravity level. What we were expecting was that we would see a monotonic shift. So as the gravity level goes up, there will be kind of a trend in one direction. What we found surprised us, which is we found that from 1G to 3G, the particle size increased. And then from 3G to 5G, the particle size decreased, which is surprising to us. The reason for that change is actually some competing effects. So I mentioned concentration gradients. I also mentioned sedimentation. Those two things can work against each other. The concentration gradient is a result of poor mixing. So as that crystal grows, you're getting changes in concentration. If your stir bar and your stirring mechanism is not faster than the growth mechanism, then you'll end up with low density and high density regions of fluid. As you increase the effective gravity of the system, in our system, we held the stir rate constant. So the mixing gets less and less effective, and you get more and more of a gradient. Because crystallization processes are so sensitive to concentration, those pockets of high density promote faster growth, and you end up with larger crystals. So as we're going from 1G to 3G, the system has pockets of higher and higher concentration that are promoting faster and faster crystal growth. And then from 3G to 5G, sedimentation starts to also play a role. At a certain point, at a constant stir rate, we're no longer suspending the particles. Once you pull them out of the solution, they're not able to access the molecules that are in solution. So you're kind of starving the crystals. They can no longer grow. So from 1G to 3G, we're accentuating the concentration gradient, driving high supersaturation is the term used by in pharma and chemical engineering. which means there's a very large driving force for growing, and that driving force gets larger with increasing gravity. But then at a certain point, sedimentation catches up and you suppress the crystal growth. And that's the reason for the inversion in the behavior. We wanted to check this hypothesis around, especially around the concentration gradient. So what we did is dissolution experiments, crystal growth, crystal dissolution. They are two sides of the same coin. You're changing the chemical potential and you're moving the system from in solution to solids. Dissolution is the reverse. You start with solids and you get to molecules in solution. If a concentration gradient is driving some of the behavior, it would also show up in the dissolution behavior because you'll have pockets of different concentration, which will change the driving force for dissolution. When we looked at the particle size in the dissolution experiments, we saw the reverse trend. So at 1G, after 40 minutes, the mode of the particle size was 40 microns. At 3G, it was 20 microns, and then at 5G, it was 40 microns again. So we're kind of seeing the sedimentation is still present, but we're definitely seeing the driving force for the change increase with G level as you're creating pockets of lower concentration. So what we've been able to show is a way of untangling not only how do crystallization processes work, which is commonly done in pharma, but we've been able to start to probe at how does gravity impact these systems. And we've been able to test hypotheses about concentration gradients and sedimentation and tie that back to particle engineering outcomes, which are directly relevant to the safety and performance of drug materials. L-histidine is an amino acid. It's not an API necessarily, but all these mechanisms are going to apply broadly across every drug product, especially on the small molecule side. So we've been able to show how gravity influences processes, even in stirred system. It doesn't just have to be quiescent crystallization. And we've been able to demonstrate the application of in situ analytical technologies, the video microscopy, the Raman and infrared spectroscopy to monitor concentration over time, and the critical role it can play in untangling how processes evolve over time. So the takeaway is, if you're carrying out activities in microgravity or on Earth, they're essential tools for understanding what is happening. And really, our hope at BARDA and what we're trying to push for is making sure that all of the microgravity science that's done pushes as far as they can to understand the mechanism of their system and try to go all the way to understand specifically what did gravity do. One of the challenges right now is a lot of data will be, here's what happened in space, here's what happens on Earth, there's nothing in between. And it's hard to know what were really the variables that were driving the outcome. Was it transport? Was it that an astronaut did it in space, someone else did it on Earth? There's a lot of variables that change. Something like hypergravity lets you vary gravity continuously, which lets you really probe the mechanism. So we're really trying to push the rigor and the depth to which the science is conducted in space, whether it's BARDA, other researchers, and we're also hoping that in the industry, people take the time to understand the mechanisms for how the crystals grow. So variable gravity studies can be an essential tool for accelerating process development studies. For the system we were working on, we were able to figure out that it was secondary nucleation. We were able to show how concentration gradients and sedimentation govern the crystallization outcomes. So even though electronic interactions dominate for determining bonding interactions, the hydrodynamics of crystallization, reactor uniformity, and the role gravity plays there can have a significant effect. And we were able to show that even for a small vial stirred at 800 RPM, gravity can still play a significant role in determining the outcomes. And this demonstrates that there's a methodology for understanding what's going to happen well ahead of the time you go and fly the experiment up in space. So kind of tying it back with space infrastructure rapidly maturing, Ken gave a great overview of some of the academic groups that are forming. There's now reusable rockets, reentry spacecraft like BARDA are now online. We can really start to think about applying microgravity to development challenges here on Earth. There's now new opportunities And if we're able to really understand what governs the reactor uniformity, how gravity can play a role, we can take advantage of the new infrastructure to have more benefits for life here on Earth. So with that, thank you very much. If there's any questions, can take a few. I know we're running a bit over schedule.
Oh, very good. Any question? Folks online, if you have a question, you can click raise hand and you will get a microphone access. Any question here?
Yeah, are you planning on testing the 0 to 1G range within the radius to look at G-dependent effects in the below, which you can't do on the ground, which you can do in your council? Are you planning that?
Yeah, that's a great question. Are we planning to test from 0 to 1G? And I agree, that's a great range because it's a very helpful regime especially for the microgravity aspect. So I don't have any plans right now, but definitely open to it. I know on the space station there are some centrifuges on board, so there are facilities out there that can start to do those tests. So a centrifuge in space is one of the ways to go to get there. For short durations, you're able to use the parabolic flights as well on the Arc.
I guess one of the things you mentioned was that it's easy for us to understand like the implications of gravity and how it's important like in aerospace. But how are you finding your communications with like broader pharmaceutical community? Like what has been working well for you there? What do you see like as like are there shifts now that you can actually publish this research?
So the question.
Can you repeat the question?
Yep, sounds good. So the question was, how are you finding how challenging is it to communicate with the pharma industry? Do they understand? Are they receptive? And have there been any changes over time? So when BARDA started, there was a lot of customer education that was required. Then there was an article in Chemical Engineering News, and we also spent a lot of time talking to every big pharma company, a bunch of biotechs. We've been at many of the conferences. So in the last 2 years, it has not been as much of a challenge as before. I think once a Chemical Engineering News article went out, within a couple months of that, plus BARDA's efforts, there's definitely still people that are learning about it. But what we find is, for the most part, we're able to jump right into technical discussions, and the scientists on the other end are pretty much up to speed these days. I think there were a lot more misconceptions 4 years ago when BARDA first started.
We actually, because one of the speaker, he cannot make it, so we do have a little time. But I think, personally, I have a lot of questions, but I think we can leave some of the questions during the panel session. So we can the next speaker to start, and during the panel session, folks here and online can ask more questions. So if no further question at this moment, you're welcome to ask during the panel session. So thank you, Adrian. So
thank you.
Yeah, you'll be in the panel, right? Yeah. Thank you. Thank you so much, Adrian. This is wonderful. Actually, personally, I also came from a material background, so I kind of appreciate the difficulties and the excitement, and you can folks here. That's why it's important to burying the gravity level and understand how would it benefit the pharmaceutical and the material research. This is vital for human to go to Leo, beyond, and go to Mars and Moon. So to the surface, lunar surface of Mars. So this is actually a very critical step to move forward. So we have a next speaker, Jacob. Are you ready?
Hey, Ken. Yep, I'm all ready.
Yes. Let me stop the sharing here so you can share your slide. 1 second.
I guess I could turn my video on too, or will it just show the shared screen?
Oh, you can turn on your video too.
Everybody.
Stop sharing. Go ahead.
Okay, I'm gonna share my screen now.
Yes, please share screen. Please share screen. Can you do it?
Yeah. I do have this pulled up in PDF. I apologize. So it might, just disregard the stuff on the sides. Can you hear me? Can you see everything?
Yes. Yes.
Okay, looks good. Okay. So hi everybody. My name is Jacob Scotch-Marat. I'm here representing Heligen Core. So like Ken said, our CEO Shashir was supposed to speak also today, but he couldn't make it, unfortunately. He had some things come up. So I'm going to be here representing Heligen Core. My background is mostly on the mission management and payload development side of things. So I spent 5 years at Nanarax LLC, where I was a mission manager, helped send a variety of payloads to the ISS, did a lot of work there. And then I worked at a company called Interstellar Lab for a year, where I was doing plant research in space. And then I decided to start my own company, which is called Monolith. It's a consulting firm. So I'm actually consulting for Interstellar Lab, my last company, and Heligen as well. So I'm on the strategy and government affairs side of Heligen as a consultant, but here to strictly discuss about Heligen and what they're working on. This is my first kind of AIAA event. So also I'm a new member, and thanks for letting me join the party here. I think it's kind of interesting, Heligen going after Varda. We'll see a lot of similarities in some of the things that we're discussing, but on a different level, I think, and a different scale. So I'm happy to get into that. So Heligen was founded in 2023 with a focus on using, basically for going away from the ISS to do faster research in platforms and really pulling away from having crew members being needed to do research. Crew time is super expensive. I think if you go on like NASA's commercial policy, it's $130,000 per hour for crew time. So any way that we can limit that crew time is important, especially as we get into the commercial space era, or commercial station era. And additionally, beyond that, I think crew time, if you have crew members pipetting and doing research and things, sometimes you might get a crew member that's a microbiologist and is very trained in those activities. Sometimes you might get a crew member that's not a microbiologist and isn't necessarily experts in it, but they definitely have training. I think, microbiology research can be kind of fuzzy, and even small little tweaks here and there can cause kind of drastic outcomes on the experiment. So really, we are looking at automation of those kind of testing material, or automation of those, analytic techniques. So our whole focus is taking that away from the ISS, from crewed capabilities, and turning it into high throughput autonomous capabilities that we launch on satellites. So we are launching currently on the CubeSat side, so about 6U. We've done one mission in 2024. On that mission, we had our multimodal culture analyzer. So really, it was a bioreactor hooked up to a cell imager. We got some really interesting data from that, growing in orbit, some cell cultures. And I'll get into some other things later, but that's kind of our focus, and it's quite aligned with what NASA is looking at as well. So major bottlenecks, we talked a little bit about, or Varda talked a bit about this already, but traditionally, in this world, there's a lot of development cycles can be very slow and costly. We don't have predictive models are tough. In space specifically, there's these major bottlenecks in throughput, like I mentioned. Right now, if beyond the crew time and everything else, for anybody that's done ISS research, let's say you kick off your project, to the time that you get to launch to orbit could take a year, 6 months to a year or something like that. And then you do your tests in orbit, and it may take another couple weeks before you get your data back, and then you analyze it on the ground, and then you decide to do another experiment, which takes another year, and that's not really that's a lot different than how we do research on Earth, which is very fast and high throughput. So we want to try to basically change that model a little bit and make things faster. Also, of course, microgravity adds all these novel environmental conditions that are very difficult to replicate on Earth. So yeah, all that to say, looking for faster validation of materials and drug candidates, organoid growth we're looking at, various biochemical and molecular behaviors in general. And all this, the goal is to make it cost effective and repeatable. So the three we have an overall vision of what we want to pursue in the future, but the three kind of systems we have right now is this analyzer. That's what we launched on the last mission in 2024. It will be on our future missions as well. And it's a cell imager hooked up to a bioreactor. And then our sequencer, we're developing it currently. That will be on we have a flight planned in at the end of this year. So that will go on that mission. That's for DNA sequencing. Goal is to also do RNA sequencing at some point, but first we're going to focus on DNA sequencing and worry about RNA later. And then lastly, the bioreactor that's kind of attached to both of these. And the idea here is to really create kind of an overall interface that I'll get into a little bit later with some of our future plans, but really want to be able to have kind of plug and play lab techniques for whatever a customer or researcher would want. So maybe you don't care about DNA sequencing, but you really want to look at your cell imagery and under microscopy or infrared spectroscopy, something like that. You would be able to tailor our kind of CubeSat platform to meet all three or whatever your requirements are for your science. So the analyzer, kind of a high level picture here. Don't want to go too far into the weeds, but like I said, it's all for automating high throughput screening in real-time data. So same as any other satellite platform, we collect data in orbit and then downlink that back to Earth. We're not returning any samples. We definitely want to explore that in the future with re-entry capsules and things, but right now we're collecting all the data, processing that on our satellite, and then downlinking it to Earth. Sequencer, like I said, that's scheduled for a launch in December. Looking for various genomics, multi-omics approaches, and the whole goal here is that kind of throughput. So we're using frankly a small sequencer that we're developing on the back end, kind of a flow cell that kind of transfers the sample through this whole project or through the whole product. And lastly is our bioreactor. Nothing too crazy here. Really, this is just developed to keep the environment stable for the sample. So that's maintaining temperature, pressure, everything else that you can imagine that's necessary. And we have various sensors in there to capture all of that. And this whole process is running autonomously with our ground control kind of managing this. And then I wanted to jump in. This will be a pretty quick presentation, by the way. But I wanted to jump into the kind of the longer term goal and where I think, where our real value here is, what we're targeting. So NASA has developed one of their programs through BPS is the CIRRUS program. It's commercially enabled rapid research. And that's all basically in line with what I mentioned about the crew time and automating this research, making it faster. So NASA has a deep interest through CIRRUS to develop these autonomous systems. I think there's actually in the SBIRs that they released and some of their solicitations that they've released, there's a lot of demonstration that they're interested in situ analysis tools. So really our focus is going to be to capitalize on some of those things that they're interested in. I mentioned spectroscopy, cytometry, cell counting. Maybe we get into developing centrifuges, but I think the sample handling in a lot of the kind of standard lab analysis techniques are really what we're going to focus on. This is also in line with the CLD and CLIPS programs that are coming on board. So CLD is the Commercial Space Stations program. CLPS is the Commercial Lunar Payload Services Program. So we don't, trying to limit crew time on both of those, of course. On CLPS, it's going to be very difficult with the landers, so we're trying to have as much in situ capabilities that we can, and also for CLD. Here's some numbers on just what we're kind of expecting with our testing. And then I wanted to talk about our launch schedule here. So like I said, we launched one mission last year, and planning to launch our second mission here by the end of 2025. Speaking with a few different launch providers on that one. And then our goal is to kind of launch every, I believe it's 6 months, or every 4 months is our goal to launch. And I mentioned this has been 6U payloads up to this point, but our goal is to kind of hit 50 kilograms in a couple, maybe end of next year. And then really start to focus on the down mass and re-entry capabilities later. This is more in kind of the mission management process, and I don't know how relevant to the room here, but my time as a mission manager for ISS payloads was you spend a year working with NASA, convincing the safety program that everything is safe and this is good, and no one on the ISS is going to get hurt. Our kind of approach to this is that we can do all of that on a CubeSat mission with far shorter kind of mission integration steps. And yeah, that's my whole presentation. So I went pretty quick, but that's our first satellite picture there, the OSW Kazora. And I should mention, so the company was founded as Odyssey Spaceworks originally, and we've rebranded to Heligen now. So hopefully there's not too much confusion there. Thanks.
So any question here and online? Okay, Adrian has a question.
Thank you for the great overview of what you're working on. I was curious about some of the fluid volumes that you're working with.
Yeah, definitely like more on the microfluidic side. I think I don't have the numbers in front of me, but gosh, I think we're like in the 100 milliliters, if that, including all reagents and everything realm. Probably less than 10 milliliters total, I would say.
Question online in person. Okay, folks online, you can click raise hand. I actually already we already gave Mike access to several of you. So if you if you are interested. Actually, Jacob, so this for you, you specialize a device, right? A device that you can do the analysis. So basically, this can be launched by any launch vehicle. Okay,
That's correct. Yeah. Anything that, so right now, like, yes, we're targeting satellites, but ultimately what we've developed is kind of this backpack that's, and I say backpack, it's I don't want to say a standard interface tool, but it's essentially a tool that we could launch on anything. It's just that we're targeting satellites right now to carry the payload. But I have every intention of launching this on the ISS at some point to plug into like an express rack or something, in intentions to launch this on other vehicle, on a lander, for example. So yeah, really we're developing the analytic tool as the payload, and then we have a satellite that's the bus around it.
Yeah, last time Shisha mentioned it can be the data can be tracked around the world. That was very exciting. There was some question in SciTech. So literally, you can you can put in the Varda vehicle, right? You can put into Varda's vehicle, or in the future vast space, you can put in their space station.
I would love to, and would love to talk to Adrian about that as well.
That's right. Yeah. That's why we're here. We're here, to bring everybody as a family. And if something happened, that would be great. Otherwise, just for, a great community. So let me see. Is this a material? Is any kind of limitation for the material? And you are talking about standard, right? So you are trying to establish an industry standard. Am I correct?
I think I shouldn't have used the word standard quite yet. Maybe at some point, but I don't think that's really the goal right now for us, is to establish a standard. I would say it's more to, develop just a specialized tool.
Specialized tool, but because end of last year, NASA has a survey, about the deal of microgravity, and they actually asked a very interesting question. They asked, should those, microgravity experiment, those things, and also the space station, now you have VAST, you have Axiom Space, you have still ISS, different groups, and should we standardize, the experiment, connector or some kind of protocol or whatever? Do you think that's a good idea, or it's better just everybody do their own? So if you want to hook up to VAST, hook to VADA, you have to change your adapter or whatever.
I think it's really interesting, and I think this was 2 years ago. NASA Tech Leaps did the it was called the UPIC challenge. Right now, Tech Leaps has another challenge available called the Payload Design Challenge or something. But 2 years ago, NASA Tech Leaps did the UPIC challenge, which was Universal Payload Interface Challenge. And that was something they were really targeting, was the development of a universal interface for all of this. Right now, like the Express Rack on the station is kind of the universal standard for a certain volume of payload. However, it's really, frankly, pretty old technology. It was built for the shuttle, I think, and then transitioned to the ISS, and now still it's here. And I think a lot of the CLDs are focused on using that standard for now because it's easy to transfer from ISS technology to that. But I think ultimately, yes, it would be good to have a standard. That's my opinion, of course. But I also could see each of these groups developing their own things. I think it'll diverge, and then it'll converge at some point again in the future as a standard. But as a payload developer, historically as a payload developer, I would love to have a standard interface that I can just take from VAST and throw it into Starlab or something, and then take it and throw it into a lunar lander. I think that's harder than it sounds, though. Yeah, and you are now in the committee. First of all, congratulations and welcome. And by the way, I just mentioned earlier, our committee has been discussing doing some white paper. So if it's something that without compromising your company business or trade secret, we can welcome to do some white paper if it's not going to help, shaping the future of the, microgravity experiment. And by the way, I'm just trying to say, all required to join the AIAA Technical Committee, especially our gravity-dependent scientific technology, is a professional membership. So if you're a professional member, you are interested in this, then you're welcome to contact us. We welcome you to join us because there are a lot of good things. You can see it's very exciting things coming up. And NASA has, as I mentioned earlier, NASA has put everything together, and they want to put, because Artemis is still going on, and we're going to Mars and Moon. And this is what we learned in the past 20, 30 years from ISS and the ongoing VARDA, VAST space, also halogen, and everybody, this thing could lead to a very explosive discovery and development. So I think it's good. I kind of advertise, but don't blame me. I kind of this AIAA event, so I say try to recruit some of the committee members and the AIAA professional members. If you are a student, we can work with you in a working group. Just mention it. And any more question? Because again, we can also ask the speakers in the panel session. I just want to say, if anything very specific for
for Jacob, if you want to ask. I don't see anybody raise hand. If so, we actually still 7 minutes to the next speaker, but we can ask Bob, are you ready to go ahead? It's not really preferred, but
Yeah, I'm ready whenever you are. So
Oh,
just tell
you're
me when.
okay. Yeah, so we can discuss more exciting issue with Jacob. I think this is very promising. With a routine launch and a box that you can just put your sample and get your data tracking. That's very promising. Okay, so Bob, you are welcome. You can start to pop up your chart. Mr. Robert Manning is actually one of the committee member. As you can see from his topic, he specializes this fluid issues and propellant. So he will tell us more about this his sharing and experience you want to share with us. So go ahead, Bob.
Yeah, let me just get everything. Let's see, share. Okay. So here. Oh,
Oh, by the way, folks, here we have bottled water in the kitchen, coffee, donut, cupcake. So please enjoy them. Yeah, sorry, it's supposed to be $2 of the nice St. Patrick Day donut. It came only one, but we still have $1. Please enjoy. Thank you.
okay. Can you see my slides, Ken?
Yes.
Okay. Okay, well, as Ken introduced me, I'm Bob Manning. I work for a company called PCX Aerosystems, also known as NewSpace. I am a propellant management device designer and their principal fluid analyst. So just have a few slides explaining what we are, who we are as NewSpace, and some, since I work for them, and then talk a little more generically about some microgravity fluid statics. So. New space, essentially, we make tanks for in-space and propulsion systems. We do some other things like nozzles and things like that. But our primary business is making tanks either for small satellites all the way up to the big geo satellites as well. We're privately held, and we work with some of the more established primes and organizations, NASA, JPL, Lockheed Martin, Northrop Grumman, Airbus, but we also work with some of the newer space companies, Blue Origin, SpaceX, Apollo Fusion as well. So we designed quite a variety of tanks, either for.
Bob, sorry to interrupt. You intentionally turn off your camera, or you want to turn it on?
Oh, I thought it was. Oh, I apologize. There.
Okay.
Is that better?
Yeah. Okay.
All right. Sorry about that.
No problem.
Okay. So we design tanks that either have composite overwrap, as the picture on the left. We also design tanks of unique shape, toroidal tanks for some very interesting applications. We also design all titanium tanks. The picture right here is not our facility, but NASA. I think that was NASA Glenn, and they were integrating our tank into the Europa Clipper spacecraft, which was just launched a couple months ago. We also design elastomeric, essentially it's like a bladder-like tank, bladder-like membrane inside a tank, as well as a rolling metal diaphragm. We also design COPVs for xenon and pressurants. I think the one showed down here can store several tons of xenon. And we also develop what they call a demisable tank. Essentially, it's a tank that's designed to burn up during reentry, so that way it doesn't cause any international incidents. So not only designing the tanks, we also design the guts inside the tank. I do propellant management. So in microgravity, fluid doesn't go where you want it to go, and it doesn't settle. And so, we design structures that are inside the tanks that manage it specifically for the mission and flow rates of interest. So 2 pictures on the left are sort of vein-like structures that sort of move propellant towards the outlet. We designed sort of complicated sumps to store propellant. Picture up here is what they call a gallery arm system or a LAD system that allows you to gain access propellant throughout the tank. And picture down here is just a zoomed in of this one over here as well. So we design it for each customer, for each application, for each mission. Not only doing design work, we also have our capabilities of building things as well. We do spin forming, essentially taking a relatively thin, up to I think 1/4 inch, and essentially heating it up and pressing it against a sort of a mandrel. You can sort of see right here what's going on. So it's a very cost-efficient way of getting axisymmetric shapes. We can do aluminum, steel, titanium, but also do weird materials that are much harder to sort of to work, such as Haynes and things like that. We also do have in-house machining, some very large vertical and horizontal lathes. We also have our own capabilities of welding, EB and TIG. Our EB chamber is quite large, 16 by 15 by 10 feet, enough to sort of fit a smart car into. It can do welds up to 2 inches in thick, so it's quite a unique capability that we have. We have a clean room, NDE, as well as our own composite winding, where we actually wind with US supplied fiber. So that way it simplifies our supply chains in that way. So, okay. Going on to more the technical part of my talk. So, why are we interested in microgravity? Propellant systems need gas-free propellant, right? They don't like gas, either to defeat either turbopumps or whether it's a pressure-fed system, gas does just not work. There's sort of 3 ways of dealing with that. One's to sort of have what they call rolling metal diaphragm, so think a thin metal sheet. On one side's the gas, the other side's the propellant, and you essentially allow this thing to stretch as or compress as, or rather stretch as propellant's drawn out of the tank. An elastomer is essentially, instead of having a thin metal sheet, you have a sort of a elastomeric rubber between the two. Each have their problems and advantages. Obviously, having those work well for very high G environments or when you're thrusting, but they have their problems. Diaphragms are largely limit your aspect ratio of your tank, whereas elastomers, obviously we pick very, very volatile oxidizers for reasons, and that doesn't work very well with many rubbers. So that's a problem there. There are candidates, but they're just very difficult to work with. Surface tension PMDs fill this gap, but we obviously had to know what's going inside the tank. Obviously, slosh is an important problem, right? If you have too much fluid moving around and your control system is trying to control against that, that could be a problem. There have been various problems that have been documented near Shoemaker, Intelsat 4, ATSV 5 had severe slosh control problems. But even where slosh is not a huge issue, if you're doing something very precise in orbit, we want to understand what's going on. Think Gravity Probe B, where you're doing very precise pointing. Space telescopes, are understanding what's going on. The propellant there is important, as well as observation, both for civilian and military. You want to know what the fluid is doing, so that way you can get onto your science quicker. Okay. Here's a nice little quick video of some simulations we've done. So you have a propellant with an ullage in the middle, give it a swift kick, and the propellant does some rather unique things. And you can sort of see here, this is in seconds. And so it's going to take many minutes for that propellant to sort of damp out. So obviously CFD, computational fluid dynamics, is a great tool. It allows us to do things that before computers we weren't able to do, but it has its limitations. First, CFD is very slow to converge to a static condition. So if you're curious where the propellant's going to be, minutes, hours later, that's a long time for CFD to get a solution, even on relatively large clusters. Also, what you do for there's what they call volume of fluid method, where you have each cell so it tracks a percentage of how much that fluid is filled, whether it's 0 or 1, as well as surface reconstruction techniques introduce small forces near the free surface. Now, for large applications, not a problem. The fluid velocities, you're talking centimeters, meters per second. But for microgravity, where things might move on the order of millimeters per second, that's a problem. And so you can sort of see right here, this is just sort of a commercial off-the-shelf software. You initialize as a sphere. A few seconds later, you get these artificial velocities that are on the order of 10 centimeters per second. And so that can really mess up convergence and your end solution a little bit. And that's largely because the pressure jump from the liquid to the gas is proportional to the second derivative of the free surface, spatial derivative of the free surface. So any small variation that's wrong is going to induce a large number of errors. There are other schemes that improve it, such as level set, or you can sort of put seeds on the free surface and advect them, but then you have problems with volume conservation. So, there's no one way to solve all these problems. You can have hybrid methods that combine the best of both worlds. There's obviously a lot of good numerics people are doing, but that are going to get it better, but it's not going to completely eliminate this problem. So when I said my title is fluid statics, it's largely because if you can't solve the simplest problem, if you can't solve statics problems, you can't really solve dynamics problems well, right? And obviously in high G, it's not a big deal. Fluid volume's its own level, interfaces are flat, life's, somewhat predictable in the fluid statics realm. But in microgravity, I think as this group knows, surface tension dominates, and then the pressure dump between that free surface is proportional to the mean curvature of that free surface. So, and so essentially, if you want something that's near statics, aka the pressure differential is constant, the pressure jump is constant, it means you have to have constant mean curvature. That means in most circumstances, that means bubbles are going to mean spherical, or the meniscus are going to just simply be sections of a spherical cap, as shown in the picture on the right. But things aren't so simple. So, Konkis and Finn showed in the 90s that you can have an axisymmetric vessel and get asymmetric free surfaces. So here they proposed having just a cylinder and then putting an axisymmetric bulge along the outside. And one would think, well, the free surface is going to be just one of these dotted curves right here, just depending on the fill level. But what they showed is that is actually non-linearly unstable. And so you can actually get these. One of the most common ones is to have a potato chip-like shape, right? So it sort of goes up on one side and then it curves up in a very sort of unique shape. And so they actually flew this on a shuttle experiment back in the 90s. I think it was back in the 90s, USML-1 with an immersion oil. And essentially they were able just to sort of give that experiment just a sort of an initial disturbance, let that disturbance die out, and essentially get all 6 of these unique different configurations just from different sets of excitation and letting it die out. So this is showing that, just because you have a vessel that's axisymmetric doesn't mean that you get axisymmetric free surfaces. And the question is well, is that just sort of unique? Is this sort of an odd academic question, or is this actually occur in things that we're interested in practicality? And Collicott and Yedler were able to show that this actually happens in a variety range of situations. In my application, if you have a tank and you put sort of a cruciform or a plus-shaped center post going from the top to the bottom, obviously you can look at that and saying, well, that has 8-fold symmetry. You'd expect the free surface to have that enjoy that same symmetry. However, you can actually get situations here where they can be asymmetric. So, what you would see here, white is sort of this gray is the ullage location, and this white region right here is the fluid. They were able to show is that, you can get perfectly symmetric situations or get these 2 other unique configurations with the same volume. Another thing that was shown is, I think this was actually proposed as another situation occurs is in propellant gauging. So obviously if you have a tank and you want to know how much propellant's in there, it's kind of difficult to do. There are a variety of different ways to do this. None of them are perfect. And so one of them was what if we put this huge cone inside the tank, and by looking at the fluid level, right, just have some sensors along the cone, then that would sort of tell us roughly how much propellant is inside the tank. Well, what Calico was able to show is that, well, you can get sort of these symmetric configurations, but you can also get these asymmetries. And you can sort of see the free surface here on the figure on the left is different than on the right, even though they enjoy have the exact same volume, right? So asymmetries can occur in symmetric vessels quite regularly, and that's something we have to look at. Another thing is if you have a sharp corner in the tank, whether by putting some sheet metal up against the tank wall or you have something else going on, that's going to change what goes on the tank quite a bit as well. Typically, if you sort of create this corner and you have a liquid here in this gray, it's going to want to flow from regions of this low curvature to high curvature, right? Just due to the Young-Laplace equation. However, this situation only occurs in very specific criteria. So I think NASA Glenn did some experiments back in the 90s where they had sort of these corners introduced into a tank. And if you had the liquid contact angle be above 30 degrees, that's the sort of how much wettability the liquid has. So a very high contact angle has very poor wettability, whereas a very low one is going to want to spread out. So here, if you had a very poor wettability, the liquid just sort of stays put, whereas here, it's going to sort of creeping along these corners. So that's something that's very interesting. And there was a further on experiment, USML2 did this sort of a similar experiment. And what they did is they created this vessel with this sort of cross section, and they sort of introduced these corners right here with varying sharp levels of sharpness, right? So this one is sort of more on the outside where the angle's much shallower, whereas this one's much sharper. I think 38 on this left one, and that here would be 20. And what you can see, I think this is 38, excuse me, over here, and this is 20. 20. And what they did is they essentially injected this as ethanol solution. And what they were able to show is, once you cross this critical angle of 32 degrees, this is for this geometry, that the fluid actually goes from where it's just not doing much to where it completely changes and wants to be more sort of completely wet these corners. So the question is, well, okay, maybe that's just with sharp corners. What about if the corner's dull? What if, there's a gap in that corner? And this still actually can occur. So if you, let's say this was, I think, done on a drop tower, you have this sort of cylinder, you have this sort of piece of sheet metal right here, and there's a gap, right, between the wall and this piece of sheet metal. And if this gap is sufficiently large, nothing happens. It just sort of stays relatively flat. But if the gap is sufficiently close, it completely reorients. So an experiment was flown on ISS in 06 and 07. And essentially what it is this is sort of a pictorial picture of what the cross-section looks like looking down from above. So essentially you have this vein, this transparent vein that sort of can rotate at different angles. And as you rotate it, the gap formed between the walls increases or decreases. And so this is a video of them filling the experiment. And them slowly be rotating it in a few seconds here. Yeah, now they're slowly rotating this transparent vein in and out. And you can sort of see at certain critical angles, the liquid crawls up the corner, and in other such circumstances, it sort of recedes as well. The video is sped up 64 times, obviously, so it's a little faster to look at. Now, one interesting thing is this, they got actually quite a bit of data on this experiment, largely because for Saturday Science, the astronauts really like playing with this experiment. So they got more data than they even anticipated just because it was very interesting for the astronauts to look at and play with. So. Okay. So the next thing is I want to talk about, how do we model this? We don't really have to go to CFD to really model all this. We just really want to know what's the fluid in when it's settled, right? When it's in equilibrium, right? And you can solve this a variety of ways. You can solve the Young-Laplace equation, it's kind of a pain in the rear because it's nonlinear PDE, very nonlinear PDE. Or what you can do is you can solve an energy minimization problem. And this is, I think, how Laplace actually derived it. You sort of said how much energy is according to the free surface, how much energy is associated with the wetted wall. That's this third term. And how much is associated with any sort of gravitational effects, which would be zero in our circumstance, but you can look at it. You can include that in as well. And the surface evolver program was developed, I think, at Susquehanna University under an NSF grant, essentially sort of solve this problem quickly. And essentially, you can initialize the free surface and then essentially just using a conjugate gradient methods, minimize this functional and arrive at what the free surface should be. So this was actually done for that ISS experiment before, and what they got is very, very, very good agreement for different contact angles. So what you're seeing here is this green right here is the transparent vein, and white is the free surface. And it's a pretty computationally efficient tool, so you can look at, different angles very quickly. And like I said, it's not just simply for very simple geometries like was shown before. I've looked at it just as sort of a cornucopia of different pictures, anything from, what the propellant does in a large tank to what it looks like in subassemblies to what it looks like in microfluidic channels, a variety of things as well. And the nice thing is because it's only models the free surface, it allows you to look at much larger length scales. So I can include, I was actually just doing some modeling where I'm looking at a fluid behavior on a meter size tank, but looking at things that are on the order of several millimeters. So it allows you to look at very large length scales quite easily. And just to show you just a little cartoon, not actually a real video of what this process looks like. It's very computationally efficient. It's just me, the video on the right is just me typing commands into this program and eventually arriving at what what the free surface looks like. Keep in mind that, as it's evolving here, it's actually not representing any physical process. It's purely numerical. And like this is not being done on a massive computer. This has been done on a single core laptop. It can be trivially parallelized and automated. Actually, I think for my PhD thesis, I had several thousand computers running, trying to characterize a sort of problem under a very large dimensional space. The software is was initially supported by the NSF grant. It's free and it's well documented. However, coding it is challenging and calls some knowledge of differential geometry. There's another program called SEFIT that sort of tries to simplify some of this, but it doesn't allow you to do all geometries. I think Stephen Collicott, you might reach out to if you're interested in looking at and modeling this modeling capability. You might reach out to Stephen Collicott. I think he has a short course available in Los Angeles in August. So that's all I have. Really the outline of my presentation was really to sort of is to really give the importance of understanding your fluid statics before jumping into fluid dynamics. So any questions?
First thing, great presentation, Bob. This is very exciting. In case you didn't know, he mentioned Collicott many times. It's Professor Stephen Collicott. He's a professor at Purdue University. is very well known in microgravity research, especially in this fluid propellant, study and other things. Purdue University has several very good programs. But anyway, as a person in LA, I have to tell you also University of Southern California, because they are also top universities interested in research as well. But any question for Bob? Any question online? Let me see if any people raise question. Excellent presentation. That's from John. That's wonderful. Thank you, John. People are very satisfied with the presentation, so no specific questions. Well, again, during the panel session.
Someone's raising their hand.
Oh, go ahead.
Okay.
Someone online want to say something, right?
So if they raise their hand, you might have to allow them to speak.
There's a raised hand. Oh, yeah. Sorry, I didn't see it. Why I missed that one? Let's see. Oh, Martin. Marty. Okay. Okay, Marty, go ahead.
Hi there. Great presentation. Thank you. I'm not a fluids guy. I'm a structures guy, and it always confounds me. Especially trying to do second and third burns. It's always easy when the propellant's settled during ascent.
Yep.
I know that a lot of people use propellant scavenging devices, for surface tension.
Yep.
And but I never really understood how you analyze that, or if it was mainly empirical.
Yeah, so I can't go into too many details just because of export control, but there is some fluid statics analysis, somewhat what I've shown there, right? You can look at it either from a 2D or 3D perspective, and Surface Evolve will allow you to look at a 3D perspective. Then there is some fluid dynamics. You would have to look at that as well, looking how quickly the scavenging device would refill. There is some parts of those scavenging devices that can be tested on ground, typically liquid acquisition devices or gallery arms, depending on your terminology. And NASA did a lot of experiments in the 60s and 70s to sort of characterize those. There's been some resurgence in looking at those for cryos, starting in 2010 to 2020. Vane-like devices that really rely on surface tension, those are largely custom codes to look at the flows in those. Wise Local has done a lot of work on that at Glenn in the 90s and early 2000s on that. So that answering some of those questions. So there's definitely some data that we're basing some of this on, but there is also some just gut feel you're trying to, when designing them, to see if they work or not.
Yeah, okay, well, thanks. It's all, as I said, it's all kind of a mystery to me, but it seemed that I know that like on New Shepard, they capture enough propellant for the landing burn in a little separate head tank and things like that to simplify things rather than having a big bulk tank that you're trying to figure out where the propellant is. And I suppose that helps.
There are other applications that have done something similar. When you're typically dealing with abort situations, yeah. Now if you're dealing like the in-space contingencies, those are typically nowhere near as severe, and you can get away with not having a separate tank for that.
Thanks.
Thank you.
Thank you. I'm pretty sure there are more questions, but we can, during the panel session, people can ask more questions because now we're actually on time, 2 minutes behind. So thank you very much, Bob. So next will be Dr. Narasimha Prasad. Dr. Prasad, are you ready?
Yeah. Oh, yeah, I'm ready.
Go ahead, please pop up your slide.
Okay. I think still I'm seeing the previous slides.
I think Bob already disconnected his sharing, so you should be able to. But could you turn on your video? Would you like to share your camera?
Oh, I'm sorry. I'm sorry. My apologies here. My desktop doesn't have a camera. I'm sorry. I'm just. I should have used a laptop, but I'm using my desktop, and it doesn't have a camera.
Okay, that's fine. That's fine. All right. So, are you able to put your chart?
Yeah. I got the charts, but it is not displaying because I'm seeing R here. From the previous presentation, I suppose.
Let me see if I can stop from here, but I pretty much sure because Bob was able to have his chart.
Yeah, according to me, I looked. I didn't. It said I'm not sharing anymore. So.
Okay, something like R is appearing here from Robert Manning. That's what it says in the bottom. I'm trying to.
From my end, I think everybody has stopped their sharing, so you should be able to share.
Okay, let me check here. Oh, okay.
Yeah, it's coming up.
No, this is the previous one. Let me hear.
I see your email.
Okay. Now it's working. Okay.
Oh, by the way, Dr. Prasad also our committee member. Just to give you an example that he's working in NASA. He will tell you more about himself. But we have Bob and Dr. Prasad and Jacob in the previous speaker. So we have several committee members that cannot make it because they're scheduled. They have to teach a proposal. Just busy. So, but anyway, we'll continue to do it, and you'll get more familiar with our committee member and what people are doing. So, Dr. Prasad, you able to find your slides?
Yeah. Hey, do you see that slides?
No, we are seeing the email.
No. Oh, okay. I'm sharing my slides here. I see that. Okay.
You have to share again. You have to click the three.
Okay.
Yeah, okay, your sharing has stopped, so I guess you are trying to share your slides.
Yeah.
Okay.
Can you see my slides now?
Yes, perfect. Very good.
Okay. Good afternoon, everybody, and I thank Ken for inviting me for a presentation. I'm a new member here. I am N. Prasad. I'm from NASA Langley Research Center. I'm an aerospace technologist working on several programs. Currently, I'm also a core and a TM on several ISS programs. So when Ken invited me to give a presentation, I didn't have much technical work to be presented, but instead of that, I would like to present what's going on ISS, what are the recent accomplishments, so that if somebody is new, they would like to know what has been done in the past year. So I would like to give a brief presentation on that accomplishments.
Yeah, Dr. Prasad, can you hit the F5 because your presentation is not full screen.
Oh, okay. F5.
Or the little icon. Did you see like at the bottom next to the bar, there's a screen icon. You can click that one.
Oh, I've done that actually. In my, it appears to me
Okay, I
full
think what
screen.
happened, yeah, if you have to share that screen instead of this one,
Oh,
but would that be okay to continue?
okay. Let me check here. Uh,
If you share again, instead of selecting this one, and then select the full screen one. Hmm?
is
Okay,
it is it okay?
no, it's the same. I think we keep going like this. Yeah, that's fine. Yeah.
Okay. Okay. So basically, I think some of the items that I'll be talking about are all well known. And for those, I am apologize. I'm just repeating this. And also, Warda has presented a good in the first presentation. They talked about the crystal growth, and there may be some overlap here. But I would like to uh, just give an overall presentation for those who are new to ISS. So while NASA regains a foothold on the moon, sustained U.S. leadership of human spaceflight in LEO is not a given after ISS, and has been investing in supply side market development for some time, but only recently investing in demand side markets in LEO to establish a foothold for the manufacturing in that environment. After decades of amazing discoveries on shuttle and ISS, and even before that is the Skylab. So ISS activities are ramping up for utilization for domestic manufacturing in addition to microgravity research. Both the government and private entities have been involved in this endeavors. And again, beyond basic science, in space production applications, they invest high value applications that meet national priorities as well as to serve markets on the earth. And so far, NASA INSPA, which is in space manufacturing program, has invested up to 60 million in concepts that are promising from advanced materials to tissue engineering and biomanufacturing. And also the benefit of NASA is to spur the economic development of LEO and to also reduce commercial LEO destination reliance on NASA as an anchor tenant. So there are three basic tenets that is for the US competitiveness in key industries that impact the national interests. And also it should directly benefit to humanity by returning products to the earth, as well as US leadership of a robust LEO economy. And NASA and ISS national labs are working together with world-class researchers, industry partners, entrepreneurs, and physicians to pave a new path in research. And there are interesting contributions, for example, for cancer moonshot. And also there is an executive order for domestic biomanufacturing. And there was in the previous administration with the CHIPS Act, as well as OSTP vision for maintaining US preeminence in low Earth orbit activities. So the main, most of the activities that are on the ISS have got three main strategic interests. One is to serve the U.S. national interests by developing materials, technologies that strengthen industry leadership as well as national security, and to provide benefits to humanity by developing products that significantly improve the quality of life for people on Earth, as well as accelerate the development of the space economy in LEO, and is what these are the three main tenets of the ISS programs. So currently they are trying to bring the U.S. semiconductor manufacturing to the ISS for higher yields, and there are several awards which have been executed, and also there are a few more in the pipeline to be executed. And the NASA and U.S. industry is expected to create partnerships that propel the U.S. workforce into the lead and to the next generation NASA entrepreneurs. Again, it has been shown that there is a very significant improvement in growth, crystal growth in the microgravity environment, which was touched upon by the first presentation by Warda. And also, I would like to touch upon a few recent accomplishments here. again, how does the INSPA implementation strategy work? And I think various, just it gives a brief outline. The NASA SBIRs, ISS, NLRA grants, as well as the SBIR grants, and also INSPA direct funded, discrete funding or direct funding from INSPA resources. And basically, they go after proof of commercial viability, and then from there, proof of production control, and then scaling in size, weight, or power, or whatever, depending on the type of um, um, product and the logistics, and then transitioning into LEO to the commercial LEO destinations. So this is in general, where NASA INSPA comes into picture, where if you look at the TRL levels, technology readiness levels, we start anywhere from 5, and where is the way, which is the just in generally called as Valley of Death, but infuses funding in that from that onwards, TRL level 5, and takes up to 8 or 9, and then the private investors take upon continuing that those. Missions and products. Again, Varda touched upon this, and I want to just have a brief as one chart which says why microgravity
I'm
works.
sorry, excuse me, Dr. Prasad. It looks like your chart is not advancing. Are you moving your chart?
Yeah, I'm moving my chart.
But on our end, we're still seeing uh, the executive summary.
Oh, I don't know what's going on.
I think that's what happened. Yeah, you have to click the specific one.
I think the presentation mode at the bottom.
No, he already on the presentation mode.
I'm on the presentation mode.
Yeah.
Just staying out of presentation mode, because then he'll see the same thing that we're seeing.
Oh, okay. Yeah, right now the suggestion is that you stop the presentation mode. Can you?
Okay.
Not then share just the chart, that what you just showed us, not the presentation.
Okay. Share screen. Window.
You stop share.
Did it come up now?
Yes, but you have to click on the specific chart. Otherwise, we won't see it.
Click on the left small one as you go down.
Click the left row, the small.
Oh, okay. I'm sorry. Okay.
Yeah. Can you start from beginning? But don't repeat the talk. Just click one slide slowly so we can go over it quickly.
Okay. Are you seeing the slides?
Yes, in space production.
Okay. Yeah. Okay then. So this is what I generally talked about, the goals and objectives of ISS INSPA programs. And I just talked about there is a significant improvement in crystal growth in space. And I also just mentioned about what the current INSPA implementation strategy is and how the funding works, where the grants come from, and where does INSPA infuse funding and we start from TRL level 5 up to TRL level 8. And can you see my slides now? Hello.
Yeah, it's INSPA.
Yeah. Okay. Great. Okay. So I will touch upon, I think Varda did touch upon why microgravity works, but in this chart it says because of the absence of buoyancy and sedimentation. Basically, the relative density of substances doesn't matter in microgravity, and hence it allows better dispersion of materials, and this helps with alloys and biomanufacturing. And it has an absence of convection, that is because of the buoyancy and sedimentation absence. Again, the absence of hydrostatic pressure on the Earth, the weight of the air exerts pressure, as well as in microgravity, it doesn't. We don't see that. So it helps in precision placement of materials in space, and also absence of container requirements. On Earth, liquids cannot be confined without the use of containers, and in microgravity, it's different. And so this has applications in semiconductor processing as well as 3D manufacturing, and so When microgravity works, for past several decades, what ISS has done for the first time is just captured in this chart. And the first one is the quantum subatomic cold atom lab. It's functional, and we're manufacturing Bose-Einstein condensates in space near absolute zero since 2019. Then there are several developments in the molecular crystal growth, crystal pharma industrial, which I will talk about briefly at a later stage. And the latest one of the interesting advancements is in growing the artificial retina. Up to 200 layers of retina, artificial layers have been grown, and I will talk about that. And also, one of the recent innovation is in Zeblon fibers, with a significant reduction in attenuation as well as the quality of the core. And that has wide implications in both communications as well as sensors. And there are programs which have involved with neurodegenerative stem cells, 3D tissues, and very interesting results have been obtained on organoids. And again, some whole organisms, plants, animals, and humans. Those are the things that have been done. And in 2024, I would like to indicate that there are four important areas which has produced advanced or significant results. That is the molecular or crystals for pharma and industrial applications, the artificial retina by Lambda Vision and their team, and Zeblan optical fibers, and again, by Saatchi Bioworks, they have come out with neurodegenerative stem cells, 3D tissues, organoids. They have generated new therapeutics. That's which they are testing right now. So coming back to artificial retina, the Lambda Vision teamed up with Space Tango has manufactured. Initially, it was 50 layers last year, and now they have gone up to 200 layer deposition in space with the quality that is required to be really beneficial for terrestrial applications. And this microgravity experiments have been confirmed with the very high quality layers, and they are now undergoing clinical trials to be validated further and to be implemented for the general public. And recently they did publish this information in ISS R&D conference. And again, the Lambda Vision can be contacted for their status, as well as the qualification process or clinical trials, as well as manufacturing scale up that are being undertaken by Lambda Vision. The second one I would like to point out is the Butler University database. They have collected, curated, and analyzed results reported on 500 crystals grown in microgravity since 1973. And they have discovered that more than 80% of those crystals, from the simplest to the most complex, and from the lightest to the heaviest, improved in an important feature from being grown in space. And this database is available for everybody to be used, and it's very interesting database with 500 plus space crystals. 85% up to 85% or more improvement in structures, morphology, uniformity, or size. And these very good applications for pharmaceutical, industrial, as well as semiconductor applications. And you could see those in that database. You will see so many crystals grown under various conditions. Would discuss the complexity, the temperature grown, the type of crystal, and other stuff in microgravity. So coming back to Zeblan fiber, which is one of the fibers which has very interesting applications with its wide transmission band, both in communications as well as in various nonlinear optics and sensors. Flawless protophotonics teamed with Luxembourg, Australia, and Visioneering teams. They have generated tens of kilometers of fiber in space. And recently they did publish that article that article appeared in Space Economy. If one is interested, one could go to that article. It has all the details of the growth, crystal growth, and the various other aspects that they had undertaken, and they demonstrated a commercial manufacturing scale up in space that exceeds the reported terrestrial commercial manufacturing quantities of Z-band fiber. In one instance, last year, they manufactured up to 7.4 miles of Z-band fiber in 16 draws in space, and so on and so forth. And these Z-band fibers are being validated by third-party vendors as well as various other entities. And I think this Z-band fiber is expected to impact several areas for terrestrial applications. So microgravity results have been confirmed, and now basically the people are trying to see how to validate independently and then induce into the terrestrial markets. The next interesting work is being done is by Saatchi Bioworks. They are trying to develop in-space treatment of space-induced neuropathology for accelerated identification and screening of therapeutics for neurodegenerative diseases. They are looking into Alzheimer's, Parkinson's, multiple sclerosis, prefrontal dementia. And in the recent results that I managed this program, they have generated a very interesting results of organoids in the last two SpaceX based flight experiments, and they are now trying to do the third one, and then they are planning to go to the clinical trials as soon as possible. Um, Again, Redwire in combination with Eli Lilly and Butler University have developed have obtained very interesting results, especially by growing pharmaceutical crystals. And these crystals on test flight of pillbox hardware, they have ongoing pillbox programs, and these crystals have been confirmed. For example, in the case of insulin, you can see that ground grown crystals on the left, and the flight crystals, the larger in size, very low defects, and also they appear to be better quality and more effective. That's is being that those studies are being done by Eli Lilly, and so if one is interested in those are the articles, as well as one could contact Eli Lilly about the status as well as further research work. The Cedar Sinai Axiom Space and Bioserve, they are invested in developing stem cells for personalized medicine. And historic first is the human adult skin stem cells have been reprogrammed in space to embryonic type stem cells called induced pluripotent stem cells. And this type of in-space reprogramming is confirmed by visual observations from multiple independent witnesses, and the quality of the results will be determined after the samples are returned from ISS in November 24th, which has happened now. They have the samples, and they are now the samples are undergoing various studies, and the applications is in personalized medicine applicable to many diseases. So these are the four very important accomplishments of the ISS programs: the Z-band, the stem cells, the organoids, for the therapeutics by Saatchi Bioworks, etc. And basically, as people have observed, microgravity is a very interesting environment which could provide more bandwidth, faster processors, energy efficiencies, new lasers, and processing power, and improve the processing powers. And especially we are now focusing on some semiconductor manufacturing like single crystal diamonds, etc. And also the focus is also on pharmaceuticals for the regenerative medicines as well as medical devices. So I thank Kevin, who is the portfolio manager for the INSPA programs. If one is interested in, one could contact anytime with white papers. And also there are some programs that have been announced. One is due soon on the ISS National Lab website, and a few more are coming up soon. As well as one can also contact Lina Harper, who is the strategic integration advisor to the ISS National Lab, and she has worked on various programs which I have indicated, which I just mentioned here. And that's all from me. And thank you so much. And if there are any questions, I'm happy to answer.
It's very informative. We are a little behind, so we can ask more questions during the panel session. So one question here for Dr. Prasad. Any question here or online? Oh, AJ, okay, go ahead.
Thank you, Dr. Prasad. It's a great overview, and the INSPA team and ISS National Lab have been instrumental in enabling companies like BARDA and the others here today. One thing I was curious about is you mentioned some clinical trials for Lambda Vision and some of the other companies. Do you have any more detail around the timeline or dates? Is it something that's happening this year or in a few years from now?
I think, recently when I met them, in the ISS R&D conference a few months ago in Boston, they did give a presentation, and they said that, the clinical studies are going, but I do not have specific timelines. The only thing I know is that they are conducting those studies, and also they are looking into various funding and other teaming arrangements. And I'm sorry, I do not have specific timelines.
Okay, thank you very much.
Okay. Dr. Prasad, this is very exciting, and they mentioned semiconductor. Actually, recent news, Axiom Space, they also invited TSMC, Taiwan Semiconductor manufacturing company, to collaborate with them for the semiconductor space processing.
Yeah, in fact, there are programs which I'm the core on that. They are trying to develop new furnaces, CVD furnaces, etc., and they're trying to work on materials like aluminum nitride, molybdenum sulfide, and also various processes involved in semiconductor manufacturing. And so I think there are exciting work is being proposed and are also being planned there. And so see what happens in the future.
Okay, Dr. Prasad, we'll talk more in the panel session. So that's
sure.
Thank you very much again. Thank you. Appreciate it.
Bye.
Great presentation.
Bye.
Okay, so now we have a distinguished speaker. He's going to talk about it's a keynote address. It's from VAST. He's our Senior Vice President, Product or Business Development for VAST Space, Mr. David Caponio. That's welcome, David.
Should I go here? Or?
Here.
Okay.
Yeah. And the microphone to you.
Well, thanks to the entire AIAA team, both the local chapter and national. Actually, Clay Morey is one of our senior advisors.
Exactly.
So
he was here. He was just here.
Oh, he was just here. We just missed him. Okay. Well, I'll catch him next time. So thanks for the opportunity. I think we participated at Ascend in both Vegas and Texas, but this is our first local event. So thanks for giving us the opportunity to talk. So this talk will be a brief overview of VAST as a company, our products, but really try to dive down into what we're doing with microgravity research and beyond. So as we talk about microgravity, I'd be remiss if we didn't mention the fact that we were originally formed as a company that wanted to explore artificial gravity. So micro, in a sense, it's less than one, but it may be bigger than zero sometime in the future. But that is the far-term vision. We're still a relatively new company, just formed in 2021, but we've been going at a pretty quick rate, and you'll see that in the progress we've made, both the team and the hardware. So when we looked at the market, what needs to exist in the near term? What is the world demanding? And that is a replacement to the ISS, a replacement of the ISS as a microgravity platform, and continuing that on as a continuous presence in LEO. So that is our singular goal as a company, to bid and to win the commercial LEO destination program. The NASA is due to bid out later this year, and award mid-26. But what do we do in between? We're in the unique position that because we are a new company, we were not formed before the bid on phase 1. So there are 3 other companies, Axiom, Voyager, now Starlab, and Blue Origin, that are on that phase 1 of CLD contract. So as a new company, we had to basically catch up. And the way we're doing that with a space station we're calling Haven 1. Now, it isn't the ISS replacement, but it will be the first commercially developed space station that will be crewed by 4 individuals. So we plan to launch that in later next year, May 2026. But to do that, we developed this roadmap both to get to the future that I talked about and to Haven 1. As a new company, you don't want your first spacecraft to be one with 4 human beings on that. So we're developing and we're currently building a vehicle called Haven Demo. That's a demonstration satellite that has the majority of our avionics, our propulsion systems, our flight software to test, to reduce risk, and to raise the TRL level of the components that you'll see that we're developing in-house, as well as ones with our partners. Talk a little about Haven 1 in detail a bit later, but that is the next step, May of next year, with a crew mission to follow shortly after that. And then a few months ago, we announced our commercial LEO destination architecture. That's Haven 2. That would be a larger space station built on the heritage of Haven 1, but one that is intended to win the CLD competition and be the replacement for the ISS. And then in the far term, 2035 and beyond, we have a vision of completing an artificial gravity space station. So what is Haven 1? As I said, the world's first commercial space station. It's as big as we can get it while still making it a single module space station launched on a single Falcon 9 in available launch architecture, and one that we could launch tomorrow if it was ready. We ended up kind of making it as big as possible for the fairing of the Falcon 9. That ends up being about 45 cubic meters, which is about 5 times the Dragon, very comparable to Soyuz, but certainly pales in comparison to the ISS that exists today. But it will have the accommodations for a crew of 4. The Dragon logistics cost is the vast majority of the cost in getting to space. So we want to make sure it's crewed with a crew of 4. We never launch it empty or partially there. So accommodations and life support for that crew complement. Also, there's a way to look out to space. We're marketing to both agencies as well as private individuals alike. So a large window for looking at space. We're actually a solar pointed vehicle. So it's a wind dome, so you have a larger viewpoint of the Earth as we're going to be changing our attitude, very much unlike the ISS. Communal data tangle, which is basically becomes a work table for our laboratory, and I'll go into that in detail as well. We'll talk about Starlink a little bit that we've added to it, and then of course, more importantly, our payload facility on board.
You should mic closer.
Okay, we'll do.
Thanks.
Also, a few months ago, we announced the interior of the vehicle. So it's a bit unique to an ISS module where it's a circular pressurized hull, and it's kind of squared off into 2 rack walls and a floor to ceiling. We did a longer corridor because everything has to be packed into the vehicle, and as well as food and commodities as well as waste. So we have a larger storage area with a corridor, but then it opens up to the other half of the vehicle into a larger diameter workspace. We call it our living room or laboratory area. Talked about that deployable table, and then the back wall is our laboratory. Because this exists with the ISS, we didn't want to reinvent the wheel, so it adopts the same standard as the ISS does. That is the mid-deck locker standard, derived on the shuttle and used throughout the ISS. We chose 10 form factor because a ISS Express rack has 10 mid-deck locker equivalents. So we're basically one Express rack is what we are manifesting in this vehicle. It's a bit spread out, but we do have the capability to do double and single mid-deck lockers, and that's for our unique thermal control in the area. You will notice it's kind of against the floor. You'll see some covers on there because there's a unique element to the vehicle we'll talk about later as well. But it allows to house and manifest the same payloads that are going to the ISS in that same laboratory space. We use the same standard that NASA is using, the SSP 57000. So it's a form fit function for a commercial off-the-shelf ISS payload can go on Haven 1. So a little bit about the laboratory. And we'll talk about a little bit in detail with the commercial partners that we have on board. Additionally, as well, in addition to the mid-deck locker standard payload, we also have the capability, much like on private astronaut missions that go to the ISS, to bring a handheld research program. Usually one that is studying the human being and physiology in space. So we have certain concepts in here about ultrasonic machines rather, but any other powered human study device could be manifest on our vehicle as well. We have a launch partnership that's very important with SpaceX, not only for the launch of the vehicle itself, but also to crew the vehicle when it's on orbit. So we have a very intimate relationship with the SpaceX team for the Dragon spacecraft. It's a couple spacecraft. It's a visiting vehicle, and we actually share some systems with them. And then additionally, for a high-speed data rate, we're manifesting some optical terminals from the Starlink high-speed internet capability to give pretty limitless or gigabit speed type downlink rates 24/7. So what is Haven Laboratory? We also, as a new company too, we wanted to use and leverage partnerships that still exist on the ISS today. So we are going out and manifesting those partners on the vehicle. We announced 2 last July of last year, actually at ISS RDC. And those first 2 are Redwire. It's their ADSEP pillbox that we'll talk about a little bit, as well as a European company called Yuri, which has a mid-deck locker payload called the Science Taxi. But basically the laboratory is 10 mid-deck locker equivalents, all thermally air controlled. Each is provided a mass equivalent of 30 kilograms. Each is provided 100 watts of power. And it is also, the crew time is allocated proportionally throughout the laboratory as well. I have a Starlink internet, of course, so massive amount of data up and down. And then, of course, with the 4 missions that we're planning, I don't know if we have a timeline chart, but each Dragon has about 200-ish kilograms, which about 100 we are dedicating for up and down mass return on each flight, each of the 4 flights that we're doing on 6 to 9 month centers. So it's very much unlike ISS, where each of the mid-deck lockers will be manifested on the vehicle and launched with the module itself. But then we'll reserve that precious mass allocation for the constituents, both needing to be refreshed and a resulting produced product in space to bring back down. We also are incorporating conditioned storage, because most of this is a biopharma-based research that will need a conditioned storage both on the ascent and descent portions. So we talked a little about our partner network, Redwire, ADSEP, Pillbox. It is up to the partner to manifest the entire experiment complement. We certainly work with them in terms of marketing that capability, but they are the integrator of the box itself. So right now they're formulating an experiment plan that spans the entire 3-year lifetime of the mission. It takes advantage of that mass allocation on each up and down flight. And since we have, it's a crew tended platform, so not continuously crewed. You have a 10-day period where crew can interact with the payload, and then you have a quiescent 6 to 9 month period where payloads can still be active, still be powered, still be thermal controlled, but they are without a crew tended activity in that period. Some have used that to advantage. It's kind of a unique microgravity environment. You don't have crew in your station. And other times it's in a more quiescent phase. Same with the Yuri Science Taxi. The unique element here is that it actually has a centrifuge within the unit itself. So both staying at 0G and then a centrifuge element that can go at various G level for both control and experiment group. And each of the units inside that kind of look like printer cartridges are called science shells, where each have a unique science project in each of them that could be changed out throughout the life of the mission. And in total, it has a capability of 36 total experiments running at the same time. So we announced a little bit of a progress update about a month ago. This is 2.5 hours up the road at Mojave Air and Spaceport. We took over the old Virgin Orbit test center, and we built a test platform that's about 5 stories tall to test not only the proof test of our qualification vehicle, but also axial and lateral loads on the vehicle, as it will see during flight. So that's in test right now, and due to be complete in a couple weeks, and that would be our qualification article. Here it is getting built. We have about 160,000 square foot factory in North Long Beach, about 25 minutes down the road. We welcome all that want to come visit. We certainly have an open door for tours. But we do a lot, basically with the Haven program, as we started out 24 months ago. We challenged the supply chain and the community who is going to be ready for this vehicle. And we made a make-buy decision based on availability and schedule over anything else. Those elements that that wouldn't be done in this timeline that we had to develop in-house. So notably, and you see here, is the primary structure of the vehicle. It's an aluminum orthogrid, plasma welded vehicle, well suited for rapid integration and a mission lifetime of 3 years. Additionally, for elements that we were able to find from the industrial base that worked out on our schedule, those we procured out of house. So it was a company in Spain called DHV. They had about 13 kilowatts of solar arrays that were more or less ready to go. So we've manifested that on our vehicle. We've done a solar array deployment test, and we're actually flying one of our 12 panels on the demonstration vehicle. We're also developing the window system. It's a bit unique too, is it doesn't have covers like the ISS, so each pane is triplicated for micrometeorite protection rather. But it gives that dome view where we can see different attitudes of the Earth through that hemispherical window. Hatch and other large mechanisms we had to develop in-house, so you can't really buy space station hatches on the market too much, so that's developed in-house. Additionally, attitude control. There's not many vendors that are capable of controlling attitude of about a 14-ton vehicle, so we had to develop our own control moment gyros. And those have been developed about a year ago, and they've been going through long life test as we speak. Valves are another important element. Life support was very unique in terms of airflow rates and constituents that has to move around. So we have a lot of valve development work. Energy storage, pretty much second to the ISS for a 13 kilowatt power station to be in LEO and go through that many cycles in 3 years. The only vehicles that's more stressed than that is the ISS itself. We're using the same cells of the NASA Strategic Reserve, but we're assembling the vehicle or the battery packs in-house as well. We partnered with another company that's local, Impulse Space, for our propulsion system. Started by Tom Mueller. They've got SpaceX fame. They've had about 2 vehicles successfully flying in orbit, so we feel pretty good about those systems. And we have in total 48 thrusters on the vehicle for attitude control, momentum dumping, and control re-entry at the end of the mission. Talked a lot about Haven demo, but basically we stuffed everything we could possibly can on that vehicle. We're watching that in a few months' time. It's in build right now at our headquarters, but it's just kind of working out the kinks for us. So ground software, flight software, attitude control, GNC system in total, more or less, and video cameras for mission assurance, and then of course the operations team. We actually have a mission control center built up in Long Beach as well that we'll be flying the vehicle from for both demonstration, Haven 1 and Haven 2 and beyond. Additionally, in parallel, the NASA program for private astronaut missions was originally conceived to spread the knowledge base of flying crew to human-rated space stations. So originally there was one bidder, Axiom Space, that bid on the first 4 missions successfully and has flown 3 of 4. But NASA, and pretty much any day now, is due to put out the next probably 1 to 2 missions out for bid. And VAS has announced our intention to bid on one or both of those missions if they have let both of them out. That will give us experience, hopefully, to fly crew the space station. We'll be operating those missions in parallel. But for this audience, it represents a second mission opportunity for microgravity research in parallel with our Haven 1. So a lot of this is, most people know as a service provider to the ISS, you procure the launch service that, usually from SpaceX, it will be in our case. We've actually purchased 2 of the vehicles ready for those 2 flights. But as a mission provider, you're the ones responsible for marketing and building a crew, but also collecting a science regiment for those missions as well. So much like our Haven 1 laboratory, handhelds in the Haven 1 as well. We also have the ability to take handheld research projects through each of those private astronaut mission flights as well. Not in the slides, but it's worth mentioning. We put out a data call with SpaceX at the early part of this year. And that was for those 3 experimental elements. Additionally, with the 4th, they were doing Dragonfly flying missions as well. Basically putting that out to the rest of the community about gathering ideas of what we can do as additional research projects above and beyond what we're doing with our mission partners at Haven 1, above and beyond with our current mission partners complement that can do handheld experiments. But we wanted to broaden the scope and make sure we're not leaving anyone behind, and taking a look at the interesting projects that we could bring on board, both private astronaut missions, the ISS, as well as Haven 1. And I believe that closes at about 1st of May. So go on the SpaceX website and take a look at that research opportunity if you are interested. And it's our kind of collective opportunity with them.
The first one is due by March 15th.
Oh, is it March? Okay.
Yeah.
So it has been expired, but I will tell you, still submit, even though that might have been a few days past. Or is it today, actually? Yeah, get it in today if you can. But try to do as quick as possible. But if it's too much, send me a note, and we'll still get you considered. Okay. Talk about Elizabeth too, PAM provider. Okay. A couple of updates we've done. International collaboration is very important to a commercial space station that will exist after the ISS. ISS is a collection of 15 plus nations. So we've engaged early with the European Space Agency, signing an MOU with them last June. We announced our research partnerships with Yuri and Redwire. And additionally, we announced an MOU with the Czech Republic last November. Then we went ahead and just buy the missions for the ISS flights, pending selection by NASA. We wanted to lean forward and start working that early with SpaceX as well. So those are kind of key updates. Our team has been growing. About a little over 2 years ago, we were a team of 30. Now we're close to 750 plus. We have a 3 building facility in North Long Beach, so we invite you to come attend. Additionally, if anyone's coming out to Space Symposium next month, we'll have a full scale Haven 1 experience for you to walk in and be a part of. All right, and we do have a video that may play. I don't know if you could click on it. If it doesn't work, we can see it on the internet later. Okay, allow. And if it doesn't, that's okay. See most of it in slides and in speech. So if it doesn't work, let us know.
It's actually coming up on us.
Oh, good. Okay. All right, give it a try.
So I'm trying to pull over.
Any questions in the meantime? All right. Looks like I'm going good. All right.
How do we make arrangements to take the tour that you mentioned at DAS?
Get in contact with Nick and I. We'll set up a tour. At the quickest opportunity, of course.
So we share the we have
Oh,
online folks,
that's
so
awesome.
we will share to the online people.
Okay. Yeah.
Does it have sound?
It does, but it's mostly just fun music. So yeah, so the interior renders, basically that's that long corridor. That's of course our company growth. You're fine, you can keep it on that aspect, but it looks bigger. The hatch in production and test. That's of course on the qualification vehicle. It passed its proof test, so at least it holds a seal. That's the dome window being installed, also successfully passed proof test. A lot of the core avionics too. So we develop our own flight computers, our own controllers, our own power distribution, our own ECLIS that extends from Dragon, the valve work that I talked about. So there's about a good majority of the vehicle that is developed in-house that's helpful for controlling our technology, controlling price and schedule, and ensuring those technologies feed in well to our next base station, Haven 2. Propulsion, of course, under test, the solar array deployments. We also have soft goods too. So all of the storage facilities inside. We have a sleep system, a crew quarters. Has a unique, soon to be patented element where the bedding actually inflates, gives the simulation of 1G, because 0G sleep, microgravity sleep for a crew member, especially the first couple of days, is pretty disorienting. So it helps them get a better night's rest. Control moment gyros in test.
Sorry,
Or just keep it.
yeah, I need to stop this one.
Okay.
Sorry for this.
Sure.
Just a minute.
All right. Okay. Is that beginning or end or where were we? Oh, yeah, just sort of in. Yeah, so wrapping up, talked about the missions, that sort of thing. So hopefully more questions we can ask on the panel, but if we're behind time.
Yeah, we're gonna be 10 minutes behind, so it's okay.
Okay.
So we allow one question while we replay the video.
Great.
So any one question, but more questions can be in the panel. So any question here?
Someone raised their hand in the Zoom.
Oh, there's a hand in the room. Okay. Second. Sometimes online people got ignore a little bit. Oh, John. Okay, very good. John, go ahead.
Yeah, what is the end-of-life scenario for this in their future vehicles? Will it be deorbited as is done now, or are you looking at repurposing options? And the substructure looks great for space scrap recycling in and of itself.
Indeed. So the end-of-life mission, the phase of the mission is basically controlled reentry. The reason for that, and the reason why we're not considering reuse is because Haven 1 only has one docking port. If you look at our Haven 2 architecture, it's basically an extended module with two docking ports for two reasons. One, you can actually have a large scale cargo resupply capacity. Whereas with a single vehicle or a single IDA port on the module, you do not. So repurposing this and trying to figure it out with a Haven 2 architecture doesn't make too much sense. Also orbitally, we are going to 51.6 degrees. We're going to 425 kilometers, so very similar to an ISS orbit. But for Haven 2, there's no NASA requirement yet. We're still kind of doing some trades in terms of what is the optimal orbit for an eventual CLD destination. NASA, along with other partners, have talked about a co-orbital location, if that makes sense, for visiting vehicle efficiency. So we don't want to tie us to 51.6 forever for that reason as well. So yeah, it's unfortunate, but a lot of the systems that's going into Haven 1 that would need to be repurposed, you'd have to have backwards compatibility, and most of the mass that's going up is consumed. So that's water, food, the waste system. So that 40 aggregate crew day is built specifically for that. Any additional requirements to extend that via other docking ports would complicate, extend the program. We really want to keep on schedule as much as possible. So we're kind of keeping a conservative amount of mission requirements and not really thinking of life extension just for Haven 1. For Haven 2, the maximum amount of flexibility in the architecture is something we're trying to do from day one. The key element with that is each module is independent to itself. So each module generates its own power. Each moderates its own thermal control. Each has its own attitude control. Each independently flies and does RPO operations and mates to the other modules. It can actually reconfigure itself. We have an architecture that's linear, and then when we launch a central module, it actually reconfigures itself. So detached and attached in another configuration. You can also envision modules being deorbited as end of life, either through planned obsolescence or potentially an anomalous situation. So you don't really have to. You can take a different posture with risk. You can take a different posture with technological advancements. We want to launch the first module as soon as possible. We want to do that without waiting for a full closed loop ecosystem. And we do that as an upgrade incrementally as we launch each module about on 6 month centers. So that modularity, treat it like a Lego brick, is very key to that Haven 2 architecture. And then try to link that up with Haven 1 for really little benefit when you've consumed all your consumables, when your laboratory equipment is kind of built for a 3-year lifetime. We didn't find too much value, so hopefully that answers. Follow up.
In the unmanned periods in Haven 1, will you have enough oxygen regeneration for mice or other?
Great question. We have a user's guide. It's publicly available on our website. I believe, and it can verify, it has a stipulation of how much oxygen can be generated and how much CO2 can be generated and consumed respectively, because the life support system isn't full up when there's not crew, because it uses some Dragon systems. So vertebrates are mostly out of the question, but small plant life, bacterial life could be considered if that is measurable and on a small scale, and the amount that's produced or consumed is manageable within the station. So we're not limited to life in general.
Take out the 40 days.
I don't want to waste that on the mouse potentially, but and we just don't have it because we need Dragon there too. Great question. Go ahead.
Thank you for your presentation.
Of course.
My name is Marshall. I have a question about artificial gravity station. I just saw the picture. It's like a long tube. How are you gonna create the artificial gravity there? Are you gonna?
It's
is it gonna consist of Haven 1 like modules, and how you're gonna rotate it to create artificial gravity?
As a far-term vision, it's a bit different from what you're seeing in Haven 1 and Haven 2. The original architecture was Starship launch modules, 7 in a row, and you can get about 105 meter long space station with the 55 or 50-ish plus moment arm. Spinning end over end like a baton, you can generate 1 G at the end that's equivalent to it with about 4 to 5 RPM. So that's the general architecture. So it's not spinning in a cylinder or like a barrel. It's end over and like a baton. And so you have 1 at the end, 0 in the center, and then you have everything else in between. So lunar, Martian, other celestial body you can think of in between 0 and 1 G. And each level essentially becomes a gravity laboratory of a different sense. So you're testing out human effects of the Coriolis effect. That's a big one. We have a objective to actually leave that architecture and take it back to Haven 1. So on Haven 1, we've designed the vehicle, we've developed the systems to be capable of probably later on in its life, and definitely the first time we attempt this uncrewed. So initially doing an uncrewed spin demonstration. For about 4 or 5 RPMs at the end of our vehicle, we can actually generate 1/6 gravity. So that is where our laboratory is. So you can envision a lunar payload that wants to be in a perfect lunar gravity well in LEO, quicker, cheaper than going to the moon, and have that perfect gravity well for a period of 7 days. So that's something that we want to demonstrate, and we're also offering to the payload community. So not only, primarily 0G for the remainder of the vehicle, but a short 7-day test while we, prove out an artificial gravity scenario on a space station, but also do that with a mission partner that wants to study something that intends to go to the moon. Okay, save the rest for the panel.
Yes.
Thank you.
That's great.
Thank you so much. So please, speakers in person here, please go ahead to the front. And we ask the panelists online, please turn on your camera if you can, other than Dr. Prasad, so people can see you. So we can add you into the screen here. Joe, you are the panelist. Yeah. Is this bothering? We can turn this off. Is a light shining to your eyes?
For us? No.
Yeah, it's okay, right?
Yeah, it's perfect.
Yeah. Okay. So we were trying to get those online to review. George, can you turn on your camera? Bob, yes, that's great. Goncalo? Very good. George?
Yes.
George, turn on your camera.
Can you hear me?
Is this George?
Hello?
Hello?
Yes. My camera's not working either.
Oh, you're not working. All right. Sorry. So we just keep it there. But Bob is on. Let's see. Spotlight. And we do have another one. Let's review. Let's see. Spotlight. Oh, so Bob and Goncalo. So George and Dr. Prasad has no camera. Okay, that's good. So because there are a couple of speakers haven't presented yet, so let's start with Joe because people haven't listened to your talk yet. So can you say about yourself? Shortly?
Yeah. Okay. My name is Joe Carroll. I'm a mostly retired aerospace engineer who kind of stumbled into aerospace in 1981, the first year that the shuttle flew. And I got to know a guy who was involved in the NASA advisory committee, and he was tasked by the administrator to figure out something useful to do with the shuttle external tanks. And so I got involved in that and learned about the wet workshop concept for Skylab. Talked to half the people in the committee that actually chose the dry workshop, and they all had different recollections on the decision. And I later realized that none of them were right because the reason they did it was that Apollo 18 and 19 were canceled, so there were spare free rocket stages available, okay? And one of them is still in the Smithsonian. You can walk through it. At any rate, that was my start, and I got involved in proposing tethers and the NASA first SBIR program. I submitted something, and 11 years later, it flew. 20-kilometer tether deorbited a payload in a targeted way so that people from JSC videotaped the reentry. Since then, I've done a variety of things, 5 tether experiments total. And I really think that the future is going to be artificial gravity, particularly Moon and Mars gravity levels, to find out how people and crops do. And I'll be talking about that later, but that's enough to get you started. Okay.
Thank you. I'm Adrian, CSO at BARDA. Just joined the aerospace industry when I joined BARDA. Before that, I was in the semiconductor industry working on materials development, and I really focus on what are the right things to make in space and why I oversee the pharmaceutical sciences team at BARDA.
David Caponio at VAST. You just heard my talk, so just briefly as a background, I think I'm the convergence of old and new space. So I started out Air Force Space Programs, and then I went to SpaceX. So and then I've been everything else in between. So ask me any questions about the full spectrum of old new space, and I can give you some Goldilocks version of what works and what doesn't.
Excellent. So for Bob, no, Bob already, but Bob, say a few words about yourself.
Yeah, I'm Robert Manning. I work for New Space, PCX Aerosystems. Like I said, I design propellant management devices. Yeah, I've been doing that for 10 years. Took over from a gentleman who's, I think he was 75 when he retired. So just to follow on that, just to keep that knowledge in the industry. My PhD was in microgravity fluid mechanics as well. So.
Excellent. Goncalo, do you say a few words about yourself? You are muted.
Okay, second screen. My name is Gonçalo Esteves. I'm from Portugal. I've been in the US for quite some time, now 8 years. Big decision to move into the space industry. Started by doing NASA challenges, in this case, the Break the Ice Challenge. Led 3 teams to winning awards. Launched rockets with Astra. And then moved into a company called Space Nation, where we are developing space training programs for civilians that will hopefully feed the demand that both David and others are bringing up.
Very good. Dr. Prasad, can you say a few words quickly?
Yeah, I am N. Prasad from NASA Langley. I've been at NASA Langley for more than 20 years. And I worked on various remote sensing systems. And currently, I'm also managing some few programs on the ISS on various some manufacturing in-space manufacturing activities. They include semiconductor manufacturing, furnace development, and various advanced material development. And I'm also interested in various related activities in developing the remote sensing systems for low Earth orbit. Thank you.
Okay, George, quickly, a few words.
Yes, I'm George Fries. I started at NASA in 1980, actually, and worked there about 1.5 years as a software analyst. And then in 99, I started again working on the centrifuge accommodation module. I was a software lead for the software they put on the controller, Boeing, and then switched over to the ground test systems where I built and maintained simulations of the space station and ended up architecting a system which actually simulated pretty much any of the payload interfaces on station. Left there in 2020 and have been independent since. When I was at Boeing, I have three patents they filed, which were awarded for appliances that could go to space, and that's one of the reasons I'm really interested in centrifuges.
Excellent, excellent. Thank you. So these are our panelists today. So folks here online. So before we open to the question, just one question to get things started. So this is obviously a very exciting era. Things are keep going very well. So could you tell us what do you see that is a limiting factor from your individual point of view? What is the limiting factor or the challenge you are facing that you hope that can be improved, resolved? So maybe we start with David.
Sure. We're at the transition, and VAS and BARDA are pretty much at this kind of front line here between, we've done it with transportation, crew, cargo, but we're just about to do that with microgravity research. And that is the transition from 100% government subsidized laboratory into a mixed commercially provided service for microgravity research. That is something unique, and I won't say 100%, but majority on the ISS. That is a unique element that our mission partners are getting used to. They have to, maybe hire a business developer to do an actual business plan, work out a cost benefit analysis and ensure that that bottom line is in the black versus the red. So it's really the opening of the LEO economy, but to go beyond the buzzword, it's making money in space and doing that with a broad area of killer apps or research or ideas that go beyond biopharma that we talk about a lot. We talk a lot about INSPA, but it's anything that can use zero-G and anything that could be produced and brought back down that's compatible with the logistic availability and cost. So hopefully that's increasing with additional providers. The cost can decrease with increased competition. But right now the ISX still exists. It's a wonderful engineering marvel and a masterpiece here. We gain a lot of knowledge from it. We have a collaboration commercial space capability program with NASA where they basically open the book and allow us to collaborate anything that exists on the ISS. But it's also something that's built for and by a government that's not built for that commercial mind space. So that is the transition that NASA is doing. They have great experience in the previous two examples, so I'm confident that they can do that. The other notable space agencies have to follow along as well. So ESA, JAXA, a lot of folks in the agencies in the Middle East that are up and coming as well, have to think in that new mindset as well. But SpaceX and Northrop have done pretty good trailblazing, have great examples so we can build upon. So I think we can be successful together. It just takes a good plan, and we're working with NASA right now to make sure that happens.
The place where BARDA fits in and what the founders saw when the company started was it's becoming increasingly easy to go up to space, but getting back down was really a pinch point, especially about making materials in space. How do they come back down? With the ISS and the cadence of the crewed vehicles, you're sometimes waiting months, sometimes close to a year before your sample can come back down. If you look at the up mass to the station, the down mass, there's a big difference in that number. Thousands of kilograms go up, typically hundreds come down. There are exceptions. A Dragon can bring back actually 4,000 kilograms, but not if you're sharing with astronauts. So where BARDA fits into that is really making it easy to bring things back at high cadence and really in that kind of low cost vehicle. It's not meant for astronauts. It can't do everything. There's wonderful companies like SpaceX and VAST for the crewed activities. But if you're just focused on making something in space, bringing it back down, where in a way where shipping can just be shipping, the same way you fly an airplane across the country for a delicate sample, bring your sample to space, run the experiment back down. That's what we saw as the big blocker for the industry. So BARDA is inserting its low-cost, high-cadence vehicle to really open up that economic flywheel, get materials up and down as quickly and the most cost-effective way that's possible. We see that as the biggest pinch point. And then, from my view, where I'm very focused on the science and technology development, I think the other big gap is on the depth of technical knowledge, and the quality of the science that's done is as high as it can be, but it's still not yet at the same level that's expected in many industries in terms of the richness of the data sets, the reproducibility. Sometimes with the space station experiment, it might get published and you see one group do it once. You don't see 10 replicates. If you want to go and make something like a drug, you need to show that it's consistently reproducible. So making sure that there's a very high bar for the quality of the science that's done, that the things that are done are truly reproducible, and that they're well benchmarked. One of the big challenges is you can have a toy model where things look different between space and Earth, but is your starting point really the best that can be done? And for something to really create value for people here on Earth, you've got to first bring your platform, your experiment, to the best performance standard that can be met in a 1G environment, and then use microgravity to push it forward. So really we see access to space as a big barrier that we're helping address. But then in terms of in-space manufacturing and production, we've all got to work together to push the rigor and the quality of work that we're doing so that it can match what industry expects for commercialization.
I think that the future of commercial and civil space, not military, is far more certain than it has ever been since we started launching rockets.
It depends on which ones and what you're getting. There are hundreds of different bikes that we sell. What are you looking to buy?
Excuse me?
There's a hot mic. Somebody has their microphone on.
Oh, yeah.
So they're anywhere from, we have a used one that's $475. Then we have ones that start to, you know, 1,000, 2,000. You have a specific one and you have in mind, you go to the internet, check it out, and then we can go ahead and you know, lead you out. We don't stock a lot of bikes here. It's all bought off the internet, where we purchase them down and then bring them to you, and we build it up for you for $125. So do you have a specific bike that you want, a brand or a model? Yes. So if you see one that you like, right, send me an email, and then we can lead you out in terms of pricing and see how much we can get it for you.
Okay. I thought he was asking.
Okay. Actually, this is a good model. Who's driving? And that's the big uncertainty. Okay, if it's going to be commercial, it's going to be the so-called invisible hand that's driving. But the commercial folks really mostly need to get their money from NASA, at least at the training level. Okay, and we have no clue as to what the beyond training level stuff is going to be, where it's not from NASA or other friendly governments. And we said 21 years ago, the then president, W, redirected NASA to exploration, away from earth science and microgravity, et cetera, put $1 billion extra into the total over the next 5 years in the budget, and said to NASA, go harvest whatever you can from other things to focus on exploration. What that did was cannibalize all the non-exploration provable parts, mostly microscience and space station, et cetera. We're 21 years into that and we haven't gone anywhere, okay? It's time to acknowledge that robotic unmanned spacecraft are infinitely better at space exploration than people, okay? Now, what does that mean we should be doing with people in space? You know, there are 80 senators that do not have NASA centers in their states. They might say, well, if microgravity is a problem for people, why don't you just send them home, save money? The real question in my mind is, can people live in space? Can we live beyond Earth? What we have learned from the space station, and I think this is the most important single research finding from all the 4 space stations, Skylab, Salyut, Mir, and ISS, is that long-term exposure to microgravity is not great for human health. We have put 50 years of research into refining microgravity countermeasures. And now we only degrade about half as fast as we used to 50 years ago, okay? I don't know that there's any other finding from the ISS that is more significant than that one. But it's a discouraging finding for anybody that's bullish on space, including me, okay? But we have to look at it, okay? The question of whether we go, my presentation later, I'll just give a brief highlight. Are we going to other planets, multiplanetary species? Are we going to the moon or Mars or both or other places? Or are we going to spinning O'Neill colonies? We don't know what gravity is enough. And until we find out whether moon or Mars gravity are enough for us, we can't really plan on a longer term future. If we find that we need more than Mars gravity for sustained human health, including birth and growth, we're going to be in spinning O'Neill's colonies, okay? I think that Jed McCaleb's interest in this, he's on something important, okay? The question of whether our future is an open one. And to find that out, we have to find out what gravity we need and the minimum that we need, what countermeasures we still need, and what are the consequences. This is stuff that we can't do in a year on Mars. This is something that will take decades, okay? So that's where we are. And the problem is that if you're going to do it with spinning gravity, we don't even know what is a tolerable spin rate to get the artificial gravity that will let us cheaply test things in Moon and Mars gravity, okay? So we don't know where we're going. And we don't even know if the invisible hand is driving.
Thank you. So we let the other speaker, panelists say that we come back.
Yeah.
How about Bob? Can you share about what you think about the limiting factor and challenges right now from your perspective for microgravity?
Well, I think a large amount of that is just the period of time it takes to do an experiment. That's pretty obvious to probably most people. Even as I'm not a professor, but I could foresee, as a professor, do I want to spend 5 years getting something to the ISS experiment that may get canceled anyway? Or even myself as doing some microgravity experiment for, some set of analysis. I work for a small company. Am I going to take half of my time for the next 10 years to get something flown? No, my company is not going to allow that. So I think what we need to do is figure out mechanisms, probably for all the sciences, just not microgravity fluids, to expedite that process, to allow another company, maybe not Varda, maybe not the service provider, but somebody like Redwire saying, I'm going to provide something for you. You just have to design the very smallest part of the experiment and fly that.
Okay, Gankalo, can you share your views about the limiting factor challenges?
Well, so I later on we'll talk about this in the presentation, but I've probably interviewed for our missions something like 400 people in the last year. And I can tell you that across many through selection process and later on train them during the missions. And what I find more challenging is a gap knowledge between if you need to perform an experiment and actually the pool of talent that we have. And if the launch cadence with the upcoming of Starship and most likely more humans to post Earth, how are you going to train those humans? What are they going to do exactly? And how are you going to protect them from the lack of gravity? So I've seen that happen. I've seen the gap of knowledge between what we have and between what even this panel believes it exists and interviewing people that are interested in space. They want to move their careers. And guys, the gap is huge. It's and we should be covering that, to be fair. If you're going to make space more accessible for all, we need to cover the gap, the knowledge gap. So I think that's a fundamental question. I've seen that also with specific things in the area of systems engineering and its application by building things, and there's a gap. So I think that needs to be covered somehow by bringing these requirements into other types of learning programs. And I have a couple of suggestions later on.
Thank you. Dr. Prasad, can you share a view about the limiting factor and challenges from your perspective?
Yeah, I think the previous panelists have excellently identified various issues. I can only add a few. One, we have to focus on developing a robust STEM force as well as academic emphasis of microgravity advances and advantages for the next generation students so that they can play a vital role. And also that the current bottleneck that I see on the ISS programs is that lack of space flights. People have got a lot of experiments to be done, and there are no space flights. The SpaceX only goes once in 6 months or so, and people are waiting to do many experiments. So there is a serious lack of availability of space flights in the immediate future, and that has to be sorted out somehow. Even though if you have a space station, if there are no space flights, that is not really good for future developments. Of course, again, there should be more private investments and space platforms that like Haven. But again, one more item that I would like to identify, which George might touch upon, is that to have variable centrifuges, large centrifuges, so that you can do some of the experiments even on the terrestrially before even taking it to space, so that you have precursor experiments done and focus on very important experiments on space stations. Thank you.
Thank you, Dr. Prasad. George, how about you?
Yeah, so having worked on the CAM and that project was canceled, what it was going to do is have a large centrifuge that you could take experiments from the BRP rack, which was like the express rack, and having run one investigation on that particular rack, then take it directly over and put it into the centrifuge to do an apples to oranges compare there between in microgravity versus gravity. And now we're in 2025, and we don't know the answers to some of these questions that I will go into in my presentation. So, and reiterating what Dr. Manning was saying about how it does take so long to get something done, and then it could get canceled in any way. I mean, we built a software for that basic controller for the centrifuge, and then it just sat on the shelf because of the shuttle crash. They remanifested everything. But yeah, it is important to understand the every aspect of doing centrifugation in microgravity, although the space station hadn't focused on that at all, because it's there to study what microgravity effects have upon biological processes and crystal growing and all that sort of thing. It's not there to study how a centrifuge might, get us back to square one, so to speak. So, yeah, that's been really a frustration for me.
All right, thank you, George. Before we continue, I just want to mention, I think one of the mentioned about the Dr. Prasad mentioned about more launches. I just want to mention, recently I saw a news. I don't know if you know Mr. Jim Mazur. I used to be VP of LJ Rocketdyne. Recently there's a news that he has become the CEO of Seagate Launch. It's a sea launch in Florida. So it's to address the question, it's not enough launches. So the company is going to fill the gap, of course, along other company. So this is really, is indeed an issue. Another thing is, AIAA, if you look back a few years, our former CEO is Mr. Dan Dambacher, who was the former NASA, in NASA working on DCX-XA, vertical launch horizontal move, reusable rocket. By the way, they were the first. The previous one was Dr. Sandy Magnus. She was the astronaut and material scientist. She was on the last shuttle flight, so also NASA people. Now we have Mr. Craig Mowry, who was from private industry, commercial space. So we can see what AIAA is trying to do. AIAA is trying to speed up the process, fill in what David, everybody talk about. So AIAA really want to help, and plus our gravity-dependent science technology technical committee, we are trying to do everything we can. The conferences, we are proposing a new journal in AIAA to cover both microgravity, physical, and the biomedical process. So we do whatever we can. So if you feel anything, let us know. We are going to be happy to help you. So any more comment on this question, the limiting factor challenges?
I realized a while ago, early days of SpaceX Dragon, Max Vozoff was hired to try to sell Dragon Lab.
I was his replacement.
Okay. Then you can test whether this fits.
Sure.
Bus companies have far lower prices per seat mile than taxi companies.
Yes.
But taxi companies make money and bus companies always need help from the city.
Right.
And it's because it's a completely different service from seat miles. Okay. You go when you want and you pay a lot more and you're happy to do so. You need to figure out a taxi level service. And I think Rocket Lab is heading in that direction. Okay.
With Mark. I don't know if you have any comments from.
Oh yeah. So I was the program manager of Dragon Lab for 5 years, so a little bit of experience on it. I think the conclusion from that program was it was just too early. Certainly, it was taking 3,000 kilograms to low Earth orbit for a period of a year. But kind of midlife of ISS. ISS hadn't really even with National Labs efforts done a good amount of commercialization. So there was really not the amount of channel providers that existed that exist today. And it was still the early part of the Dragon program as well. So it wasn't regularly flying to the ISS. And so that was a couple of market forces. It didn't make sense. Could a bigger vehicle? I mean, BARDA's
smaller vehicle.
Yeah. Could have. Well, the smaller vehicles are working, and BARDA's living proof of that. And there's others in the market too. We won't mention them, of course. Competition. But can a bigger vehicle do it? There's a couple in the works. There's an ESA program called Space Rider. There's a couple that are derived from that technology as well. But they haven't flown yet. They haven't proved a business case yet. So that remains to be seen. So right now, rideshare launch is prolific. Not much microgravity research is dependent on inclination. So you can pretty much just launch to anywhere in LEO and get the same results you want. But yeah, could a bigger vehicle? Some people have announced plans to do that with some visiting vehicles that are being developed for cargo resupply that we work with. Have aspirations of that too. Hopefully the market gets bigger where the bus is able to make money too. But right now, early parts of the market, the launch opportunities with a 500-ish kilogram payload, total spacecraft mass with payload fractions smaller than that, works now today. So that's good. We have a good foothold that the taxi is making money. But if the market increases a little bit more, maybe the bus makes money too. Just didn't do it in 2015 or 20.
Well, part of the problem is you have to get everybody to the launch pad the same day.
Mm-hmm.
And when it's one customer, it's easy.
Yeah.
When it's 10 customers, it's impossible.
We feel very fortunate that there's a bus to go up on the rideshare. We're one of 40 or 100 satellites, depending on what's going on. And then having your independent vehicle that's not still on the bus lets you come back down when you're done. So if you're running a time-sensitive experiment, we have the flexibility that we can run our experiment just before we're ready to come back in. So we can at least go from experiment completion to reentry within a few days or a week. But of course, the lead up to that, we still have to wait to board the bus, wait for all the passengers to get on the bus. So it will be nice to get more flexibility on the way up over time as well.
And the other key factor there too, we agree a lot with BARDA, but we also differentiate as well, is the inclusion of a human hand. And there are applications that work well in automation and applications that do not. And there's a question of scale. Does the scale work better without human beings or without? So that's market forces that we have to figure out. But that's another key element as we're looking to just make stuff in space. The question is, could a human tend a large scaled up laboratory in a human tended vehicle? Maybe. Can it be done quicker and better from an autonomous platform? Maybe as well. So we're trying to figure that out.
Any comment from the online panelists? Well, if not, we're probably open to a few questions from the audience. But people, I want to say, because you mentioned Rocket Lab, which happened in Long Beach as well. It's also within the LA section, which is very important. And David mentioned about the collaboration with Impulse Space. Actually, we just have a tour when Clay was here. He was in the tour with the students. So we have 4 student branches: USC, Cal State Long Beach, UCLA, and UNLV. So we are also kind of incorporate local student activity. So this area has a full of talented students and also a lot of workforce used to work in space project, aerospace project in this area. So LA area is very interesting. So, and I talk about the bus. Actually, there was news talking about Rocket Lab. They have a new bus system. Actually, they said it's the only one that is quite competitive towards SpaceX. So it's very exciting. Okay, so if online panel has no comments, so we are open because of time limitation. We want to open a few questions only. So anyone online or in person, you want to ask a question? Can you speak a little bit louder?
Yeah, I'm not sure the folks online will be able to.
They can hear.
But okay, cool. Hi, my name is Homan. I'm just here as an individual, but I do happen to work for Virgin Galactic that provides suborbital microgravity. And so what I'm curious about is, do the shorter duration suborbital flights have like an integrated place in the sequence of how people are running experiments who may, do their experiment on a short duration suborbital flight first and then go to the longer duration one? Or is it more of a different customer base?
I'll start off quickly and then hand it off. I think there's room for every platform, whether it's hypergravity, parabolic flights, drop towers, and I'll just speak to pharmaceuticals. So people have learned things on parabolic flights. For industry processes, you're often running about a 24-hour process, whether it's a small molecule or protein crystallization, and sometimes for like structural determination, you're running for weeks. So you do have limitations depending on the purpose, but there are some examples of protein crystallization even on parabolic flights that people are attempting. So there's certainly room for it.
Yeah, it's not different at all. It's just a logical step of from a drop tower to suborbital flight to an orbital flight. But some of these phenomenon just take more than a few minutes, and they can get some maybe screening process done as a quicker and less expensive suborbital flight to really hone on their project in a more efficient manner for that orbital platform. So yeah, we welcome the pipeline from Virgin and Blue Origin as well. We think that's an excellent. You both have developed that experiment pipeline, and we're kind of using the same trailblazing even through NASA centers too. Like there's a flight opportunities program that's pretty much built for a suborbital platform, and we're talking with NASA and say, I think orbital platforms are coming along with us in Varda, and we should make that part of that too. So it helps the government and the research community to think of what's next. The successful project that needs to be in the microgravity environment for longer has the eventual budget to do it on an orbital platform, and then just feed right in there. So we welcome the step that they can take suborbitally.
That's where standardization will become important. You don't want to have to change gears with all your hardware when you go from one provider to another. I think it's natural that once that begins to happen, there will be a powwow of the different parties.
Yeah, that's a good point. So I talked about it when we're building our laboratory. We just made it look like the ISS. asked that of Virgin and Blue as well to make sure that there is that easier pathway for the channel provider, the research provider, to not have to redesign their system. I think they're there. I can't answer that it's exact, but our intention was to mirror the ISS, and we find that to be very successful. Now with CLD, with the future of the ISS, NASA's thinking about, oh, is there a better common standard? Haven't seen an answer with that yet, but we're helping them out, us in the competition, to make sure that's good. We should have a common standard that works on all platforms. NASA's intention is to have 2 CLD providers in orbit. So if you have a VHS and beta, that would be a very inefficient way to watch a movie, and the same goes with science research. So we welcome the standardization. We hope it's something that's the most efficient between the platforms. If it can evolve from the mid-neck blocker standard, maybe, but there's been attempts made, even the ISS. There's like the European ISI standard that didn't really take too much hold. So try it. If it works out, that's great. But NASA being very collaborative and making sure that we're all building to a common standard, make it easier for them to manifest payloads on.
In the early days of the CubeSat world, there were actually 3 container standards that were incompatible.
Right. So any comment from?
Yeah, from a fluids perspective, I think there was a big step change once we started going to suborbital. Largely, drop towers are just too short, and the parabolic flights, the G levels have quite a bit of noise associated with them, and so going to suborbital was sort of a good blend in the sense that it's pretty low acceleration levels, G jitters in the order of 10 micro Gs, 100 micro Gs, and the fact that you're talking about 40 seconds, because quite frankly, for most fluids only experiments, you're going to have to scale it down anyway, typically, and so scaling this down all of a sudden makes everything faster, whatever physical phenomenon you're dealing with. Now that being said, you start combining fluid thermal, then a lot of those scalings break down, and then I think that's where orbital experiments in orbital make a lot more sense.
So any more comments from online panelists? Okay, if not, we move to the next question. If anybody here online, I saw there were 2 questions. One from Emeka, I think one from George. Do you want to speak out?
I'll go. Hi, everyone. George Weinman. I am curious about the cost of flying. So we've talked a little bit in some of the presentations about the cost of coming down with launch and potentially still bottlenecks on availability of supply. But given where we are today, in someone wanting to fly and pick your payload size, 10 kilograms or whatever the right metric is for you, where are we on costs, and where do we expect that to go as your systems and capabilities mature?
So I could start with BARDA. So if you look up flight opportunities, BARDA is part of that. And the way you can think about it is we're probably one of the lowest cost vehicles that goes to space and back. And then we try to think about it as different slots on that vehicle that we can offer to partners and customers, whether it's on the outside of the vehicle or interior payload that needs power and to talk to computers. And so really what we're starting right now is kind of the most expensive for that vehicle size it will be. And then year over year, we're finding ways to continue to drive down the cost. And then over time, we'll have different vehicle architectures that allow us to give kind of a better dollar per payload. And we just try to optimize what's the total mission cost to try to keep it as low as possible, but then also think about it in terms of cost per payload. So, we don't publish too much in the specific details, but if you do want to get in touch with us, I can link you up with our BD team that can go into the specifics. But if you think about like a Dragon versus a BARDA, it's a huge change in the total mission cost. Of course, we're also a much smaller vehicle. So if you think about it in terms of dollar per kilogram, you definitely get advantages with the large vehicles.
Our main competitor today is, I wouldn't call it a competitor, but just the only crewed orbital platform that exists right now is the ISS. Other than Tiangong, but limited access, of course. So we can't be more expensive than the ISS. Researchers have the choice between going to us and them. There's a little bit of a capacity issue on the ISS, limited life. We're a little bit open. We're just kind of, new to the scene. So we had that additional capacity. So that's helpful, but we really couldn't charge much more in all than the commercial NASA price. So that's where we stuck our price. And it's been relatively well received by the community, and they've been manifesting payloads just the same, because we do provide something unique. We do provide an expansion. We didn't want to charge more than they do on the ISS.
So any more comment on the online panelists? Okay, if not, George, does that answer your question, George?
You will. Obviously, it'd be nice to know. I mean, we all talk about, for example, small sats on a small launcher. They're all publishing a target goal of $8,000 per kilogram. So it'd be nice to know if there was a metric out there that we can sort of understand where we are today versus where things are going. I guess the ISS, I actually don't know what a commercial price on ISS is, but it'd be nice to have an idea of where we think that is headed. Was it simply that we're increasing accessibility, or are we eventually going to see systems that drive costs down?
Yeah, that sounds good. So I can expand a little bit. So the way you can think about the ISS is it costs a few $1 billion per year to maintain the entire platform. And then you also have the transport costs. So I don't know the actual cost, but to bring a Dragon up is probably somewhere around 200 million plus or minus 50. I don't have the actual numbers for you. And you do 2 of those trips a year. A lot of that $3 to $4 billion per year is the maintenance and supporting life, transporting astronauts. And then the commercial ISS prices, depending on how you look at it, there's the unsubsidized cost. So you think, what is the total cost the US and all the governments pay to keep the station online? But then there's also the subsidized cost. So I think NASA has some published numbers where it depends on your payload and requirements. If you're doing a powered payload that requires power on the way up and power on the way down, it might be something like $60,000 per kilogram. I don't have the actual number, but if you do unpowered, it can be less. And you can also drop the price if you don't need to come back down. So if you just need to go up, you might be at that $10,000 to $15,000 per kilogram or lower. But if you do need more capabilities, it's just a higher cost. And maybe someone else can add the actual numbers and specifics.
My aerospace mentor, Jim Arnold, who started the chemistry department at UCSD and did a lot of moon rock work, he said that if you have access to all the accounting data at the end of a mega program and try to figure out the cost per unit service, you can only get within a factor of 3. Because everything in the project, if it was a big project, projects that are funded for other purposes feed into it, and things that are funded by it have nothing to do with it. Factor of 3 is when you have all the numbers.
It's still, logistics is still the biggest portion of the cost. Ours is bigger than Varda because they control the capsule cost as well. But they're still flying on SpaceX rockets, so we're beholden to that. They're pretty good. They're pretty cheap, like the cheapest they've ever been. But as a customer, you always want better. So we welcome the competition if everybody's up to it. Haven't seen too much yet on an efficient per kilogram yet, but the future has a lot to hold. Starship is an order of magnitude, reducer of per kilogram cost. Can it be efficiently employed, to deliver logistics to an orbital platform? That remains to be seen. I was doubtful on Falcon 9 rideshare, and it's been a smashing success. As the first kind of mission manager on a rideshare mission on Falcon Heavy, I can attest it was quite difficult, but they've got it down to a science. So can Starship do the same with, like I said, another order of magnitude higher of cat herding and making sure everybody shows up to the bus on time. But hopeful for the future, and maybe those unit of size just becomes bigger, so there's not much moving parts to all load on a vehicle. But we're hopeful, and competition helps. But right now it's pretty good.
So it's okay for one more question, one last question. So Emika, so can you speak out of your question? This is the last question. Can you kind of speak out quickly? Emika.
Can't unmute.
Oh, sorry for this. Let's see. Oh, here. So I sent a request. Okay.
Yeah, I just got it. Thank you so much. So can you hear me?
Yes.
Yes.
Yeah, so my question was like looking from like a policy perspective. Are there things like maybe like regulatory things that you feel could help support like microgravity and space station research? I know some of the stuff that China's been doing, they kind of work in concert between the government and private industry. And I know we've kind of given a lot of flexibility towards the commercial sector here in the US, but are there any kind of policy shifts or changes that you think would help support microgravity and private space station research moving forward?
I just have a quick one for ISS. One of the things that has been highlighted by some of the oversight committees and reviews of the policy is that the intellectual property positions aren't as clear when you're doing work on the ISS. So the fear for a commercial entity is if they generate some IP and they want to file a patent, will they be able to control who can use that IP or not? And right now it's not super clear to commercial entities how much control they have over that IP, or whether or not the government reserves the right to have access to that IP, whether or not the commercial company wants to agree to it. So for pharmaceutical development, that's actually quite a significant barrier, because drugs, once you make it, you can measure what it is and reverse engineer very quickly all of the values in the patent. So if you're doing something on station, you discover a novel crystal form, you patent it. If there's a backdoor to that IP, it's very difficult to have a sustainable business, because now you don't actually fully own the thing you're supposed to own to be able to take your drug to market. So I think the one thing I would highlight is just getting everyone very clear and aware of what the IP rules are, and if there are issues on that IP, making sure that companies are empowered to fully patent, and maybe they have to pay a different price to use the ISS to get there, but just leaving that room open so that the innovation cycle of the particular industries can run unencumbered.
One of the biggest, or one of the most unique regulatory element for a crewed space station going forward past the ISS is this intergovernment agreement. And I'd be remiss if I didn't mention that, because that's AIAA's present pretty good passion project here. We're interested in continuing that. We don't have formally in position just quite yet, but that's something of incredible interest to us. And then everything else that goes with it, regulatory for FCC, for NOAA, for reentry licensing. Obviously, Bart can talk about that a lot more than us. But all of that has to be, a smooth process, as it is now for commercial launch. It has come a long way. I started in launch when there was no commercial launch, and when you can launch multiple times a day, that means it's working. Let's do the same for orbital platforms too. It's worked well on the ISS. The liability issues it's quiescent more or less, and it should be that for CLD. So figuring out a construct that works with multiple commercial providers from multiple nations, still with a large NASA utilization within that architecture too, there should be a future of that, and we are working hard to make sure that that's in place.
All right. Any comment, online panelists? No. Okay. Because we already extended the session a little bit. Obviously, it's a very exciting conversation. We could continue But we'll keep doing this. This is the first time we do this. I think we're going to grow it. As I mentioned, we did this space architecture technical committee. Eventually, we have 230 people, online and in person. So we are trying to explore this, and we can see how to grow the awareness and help each other. The AIAA here is, for everyone, for every one of you. We'll do the best. So if you any information, anything you need, please let us know. And we're also going to have more like webinar or journal or white paper, those things, anything we can help. And the standard, those things we can definitely help on. All right, so let's thank the panelists again. This is a wonderful conversation. Appreciate it. Thank you so much. Yeah, thank you, thank you. So, so our next speaker is Gankalo. So, are you ready? Yeah, thank you so much. Thank you, appreciate it. This is wonderful. Thank you so much. Excellent. So, Gankalo, would you be able to share your chart? Oh, sorry. All right, so you can share the chart. That's good.
Let me know if you guys can see the screen. It should be something in purple saying bridging the gap training for microgravity readiness. Is that something visible?
Yes.
Okay, fantastic. So a bit about myself. I'm Space Nation Chief Experience Officer. Essentially, I take care of all the both sales and marketing, but also the interviewing of candidates, the processing their training experience, and then post mission, how can we continue to help them? Space Nation is located in Midland, Texas, in the only spaceport that combines both commercial and future space launches. And we've been doing this right now for a year. Although Space Nation has been around for more than 12 years. We started effectively training people on space capabilities. So I'm going to present to you what's been the experience so far. There's a set of stories, but also very critical things for what the group does as it comes from day-to-day work. Okay, essentially, Space Nation's, let me make sure that you guys can see this. Space Nation vision is to evolve into a thriving community of universal citizens. We do have a curriculum for what would be universal citizens, especially on Earth, Moon, Mars, and beyond. And the greater mission is to establish these communities beyond Earth and human-led industrial operations across the solar system. We need to start training for that. Independent if we go in with 1 new cylinders or something different, but there's a big vision over there. We do want to connect people on Earth across the whole landscape for the life-changing benefits of space with everyone. And this becomes more actual when effectively do the training. This is an example of our sample instructor cadre. Besides Greg, Box Johnson, Terry Verts, and Mike Bueno, we have Special Forces members in our crew, a set of people that have been working in space. And those are the ones that provide in situ training to our crews. What we do training. We do space training on Earth, but they are effectively life-changing experiences as our participants move from. I've had the dream of space. I've been working on this, but I don't really have contact with the hardware. I don't really have contact with the mission context. We do that. We do that on a regular basis. Effectively, we design and deliver the best experiences out there. We have realistic frameworks and scenarios. Everyone in the team is extremely passionate to what they do, and we do maximize end-to-end the value of the investment for our customers. This is an example of a crew. You guys will see that the ones in purple shirts are the crew members. They come from all walks of lives in different countries, and the folks in orange shirts are trainers and mission support. But But I do want to highlight the diversity of the teams that we've trained so far. People coming from Turkey, from Finland, from completely different countries to train with us. All of their feedback is life-changing, transformative, and unforgettable. We did have a mishap, a giant mishap in our mission, in our first mission. Our moon simulated environment in probably one of the unique events in Texas that was a hailstorm, never happened in like, I think 12 years. We had a hailstorm, everything was destroyed. And then Mike Good, the astronaut that was in charge of training, he said that he didn't know how we could pull it off, but it does happen when you're on the ground. And I would say when you are in Texas, that's a different state as I tend to live with. This is, so what I'll present you next is the lessons that I've learned so far in the Earth-based training leading to space adaptation. That's one of the high altitude chambers that we've helped our participants have acquaintance with, and also some of our test equipment. So this matters because microgravity presents unique challenges regarding adaptation. Mostly, I'm talking about mostly for human space flight, and so a bit different only for talk about looking into sample objects or test subjects, but we are looking at, okay, what's going to happen with humans? And this is what I've observed during the training and how it translates to space readiness. I'll tell you the gaps immediately, because if the other one, something that you guys are going to take right now is, this is what I found. So essential leadership and decision-making for anything that has to do with mission design and operations. Look, both the participants, also the curriculum that is out there provides tremendous challenges. What to do if there is a leak, what to do when there is some kind of storm. So humans are not geared yet to work in that manner. So we found a lot of challenges in making sure everyone is aligned and can work as a team. From the systems engineering side, both having people coming from space architecture, both like really good systems engineers, but when you pick up and say, okay, these are the parts, this is the manual, this is a new team, how can they operate? Big challenges over there, but also interesting opportunities. And then we guys talked about also the physical side. So I'm responsible for all the physical training due to my extensive career in martial arts and as a competitive athlete. And I can tell you that the humans that we want to place in space do need to be re-engineered, not only from the physical side, but also from their mental resilience. And then there is a lot of questions regarding communication protocols, not only the utilization of equipment, hardware, but also how people communicate in some of these high pressure environments. Clearly, the mentorship and guidance paths, and it's good that AIAA exists. I started in here several years ago. It has helped me tremendously. But the mentorship and guidance paths coming from people that have worked in space or have lived in space, I see that I would say that they need improvement. Space Nation training overall process, so that when people come in, is they have an extensive onboarding where we select the applicants. We do extensive leadership questionnaires and psychological analysis. We initiate their training in space systems engineering, but that's in the onboarding. During mission training, they go to an intensive training in leadership, problem solving using space operations. In this case, we have a simulated moon mission where people go both in what's a simulation of a moon base, but also the mission command. And we do try, and the participants do acquire some good operational transfer from that. Post onboarding, we continue supporting the participants because we take tons of data, even physiological data from the participants, but how do they operate under stress conditions? We do support them. We do provide capability gap assessments and support. Essentially, guys, you want to know more about let's say, data management or in this thing that you guys saw in my background, ISRU, and so we do support them moving ahead with their capability development, and we continue that mentorship. So it's an overall structuring. We found this opportunity in the market, to be fair, and we provided a comprehensive end-to-end process. This is what our customers are saying. Leonardo is a well-known space architect. Milka works for the Permanent Basement University, and they found this transformational. The fact that they could put hands-on experience and get mentorship and direct feedback was fantastic, to be fair. HR Zucker is someone from the times of the Apollo. He's seen Apollo launches and just tremendous experience with us. But I want to give you this. So this is how we started. Okay, we had this initially for 1 year of missions. We had roughly 1,200 initial applicants. Overall, we did 417 second phase interviews between myself and other crew members, and we selected 31 people to come to these missions. So in terms of numbers, gives you an idea of this is the type of interest that is out there, and also how extensive the process is. But these are the key challenges that we've understood over time. The talent pool lacks significant key skills. As we've interviewed people, we could see tremendous changes, or at least I'm going to say need for capabilities in terms of systems engineering, overall science knowledge, and others completely in the extreme. Like we had people coming into the missions with already very much a pathway connected to an astronaut path, and they still did the mission because they require the operational knowledge. The selection rate, if you guys want to think about, if you want to think about that, in 5 years, we want to launch how many? 1,000 people to space, or 10,000, or like there is out there 1 million. It's really unrealistic. How are we going to train them? What funding do we have? It's very, very. The sample size that I have and the knowledge that we have so far brings a clear need for more capability development. So there are more things that we need to know about that. These are essentially the key challenges, or translating this to the lessons. So how are you going to manage a crew in microgravity? Yes, we know it from the space station, and although we've stipend all the reports from the ISS, and I've worked at least in a good project for the ISS, how to manage crew presence, how to manage payload and experimentation. It's still not completely aware for, I'm going to say, for a large sample group, not for a small sample group. That's what we have. And clearly, how do people make decisions? That's something to definitely work about. In systems engineering, we've seen here, Alex is our leadership trainer. We effectively have all our candidates putting their hands on tools and working together to solve problems that come from the fact that as an astronaut you will be doing jobs. You will be working with your hands, doing EVAs and even before. So again, knowledge of systems engineering prior to that, it's definitely important, and it needs to be maintained, and in this case further. I cannot overstate this. I do physical analysis. I do the physicals for everyone and the testing, and either we find a way to go to beyond Earth that replicates our gravity, or the existing physicality of our participants and mental toughness needs changes. And I've got good data on where it is now and where it needs to be going. And I would say the last one is everything that is to do with Capcom or communications in this environment needs a furthering of, I would say, the standards and also the execution. It's when we are in the missions, I see big changes in the way that people communicate with their crew members, and then later on, as they change this into their lives as well. Takeaways from you guys, for us. This Earth-based training provides a foundation, but microgravity does introduce completely new challenges. It's completely different. It's different because we do need to start thinking about how are you going to train all of these workforce for microgravity. Leadership, system thinking, and adaptability are crucial. And we can break this down, each one of the components in leadership, from followership, that's one of the components, the team ability, and then the fact that you need to look at these things as a whole system. And I found that's something that's not been propagated enough. And there is a need for a continuous refinement of training methods, but I would say even standards, because right now, if you look at commercial standards, it's very hard to derive which one. You can say, oh, I've got the NASA one. Yes, of course. But we're talking about a 3 to 5 years period of training compared to, oh, okay, someone is going to go up there for 2 weeks. So there is a lot of work, I believe, that needs to be done on there. Specific recommendations. I mean, really, I try to nudge it down as much as possible with our mission participants. You need to expand for more microgravity simulations. We currently don't, at least in our company, don't have them. Probably David will have them and others, and I've seen that in the panel, or at least in the participants. We have other companies in here, so there is the need, I would say, to expand that. The mentorship code, the mentorship programs are not there. I've not seen them. So essentially, not only, I've received a lot of needs for technical roles, but when I assess people during the missions, it's not the technical side that is lacking. It's the whole ability to be a leader or to be a follower. So that thing is not being worked enough, at least from our sample. That is across the US being here. And then developing stress testing scenarios. We've started with almost, say, 5 of the ones from the ISS, but we do need to develop more in that sense to become, I would say, an overall standard. And we definitely will need to, there are more experiences or potential things like what we do. They don't focus as much in this overall end-to-end approach of training, but we do need to connect more other experiences to support this. And there is a big thing we started already with having AI agents, and we can extend that to robotics, but what are we going to do with that? So we need to kind of pick up each one of these 5 layers and start developing them. So overall, as after 1 year, interviewing many people, being in all the missions, deep down into how do people execute their work, seeing the astronaut mentorship, seeing their lives transform, and this, what my view is, microgravity, our group in here can provide tons of requirements to support this space workforce development, but there are 2 key components out there that I haven't seen yet enough. Both one from the side of the funding. We are a private company. People pay to come to our services. Or their companies help out. But if this becomes more large scale, hey, how are we going to find this? And colleges move too slow. That's the reality. And in case also the fact that we need infrastructure, not only back in here close to me in Philadelphia, there is NASTAR, but if we want to train people, where are we going to train them? And of course the how is something to be discussed, but we already have an astronaut readiness program that is working well. So the need for space work and work developed is urgent. And guys, this is empirical data. It's this observation on the ground. So we need this targeted, probably more data and more cooperation to get more specific data and what exactly are the skills and methods to do this. And they'll leave you, this is the first team, this is the last team. As you can see, there is I'm going to say a change. More women are coming into our trainings. So there's something also to think about. That is how diverse in terms of knowledge and participation we want to be. We are diverse by capability. That is, we want people that really want to work in space and train, and we see that as a good way to cover knowledge gaps. Yeah, so I'll leave it there. If you guys have questions, please go ahead.
All right, thank you. Any question here online? If not, I do have a quick question. You are the astronaut training program, right? We actually got this question several times. So did you give out, if a student get trained by your space nation, do they get some kind of advantage or certificate? So if they want to become Blue Origin or ESA, NASA, SpaceX astronaut, do they get some kind of credit or make it easier for them to become astronaut, or is fully qualified for join those missions?
Yeah. So being very clear, we are a commercial space training company, and I can only give you what we've seen with our participants, that both the experience, the gaining confidence that they have, and their exposure, and then their work, because they work massively during the mission and post mission. And also our certification has helped them to garner jobs. That's it. Because being clear, I've not seen yet anything that would say, put this certificate in here from any other places and you'll get a direct job into NASA. I can tell you from the pool of our participants that our work has helped them to move ahead in their career and their jobs.
Yeah, understood. It's just a typical question we got from members. It's just a standard question because they have been asking where they can get the training.
Yeah.
You understand?
Yeah, we provide the skills. That's the from the missions. They get trained by astronauts, by the special forces. They have a new crew. We provide them specific roadmaps in their career developments. Yeah.
Excellent. You see, John actually have a comment say it's a great idea. So people really like what you said. That's very interesting. All right. So any further question? Okay, one is.
Hello. Thank you for your presentation. I have a question about the health requirements for, when you qualify people to go through your program, did you check their health condition and what are their health requirements? For instance, if a person has, I know for like jet pilots, there are very high health requirements. And I think for astronauts, it should be something the same, like maybe a little bit lower. So for instance, if you have like a broken nose and not super straight, like back spine, maybe you have scoliosis or something, is it gonna make it like impossible for you to become an astronaut?
So not for our program, to be fair, because think about this. And this has been a problem, I'm going to say a problem in the industry, that is, the only thing that you can do in space is to become an astronaut. No, man, there are more things. There are way more things that you can do. In this case, for our program, what we ensure is that they got their physicals done, and there are a set of specific requirements in terms of manipulating load, and the fact that the mission is intense during these 3 days and then before. So if you get your physicals done, if you are in good health, but if you are in good health and you pass through our requirements, you should be able to meet our physical requirements. We do provide specific training plans prior to the mission in order that you get prepared, both mentally and physically, so that you can get the best of the experience. So, yeah.
Thank you.
Any more questions? Folks online, I don't see any question online. I personally have more questions, but I don't want to delay the presentation by George. So if any more question, please welcome, to contact Giancarlo. I think it's a very exciting program. Yeah, thank you very much, Giancarlo. This is great presentation, great program.
That's very exciting. Thank you for your sharing. I think more people will know about it through the recording. It's very important. Thank you very much. Thank you again. All right. All right. So next speaker, George, are you ready?
Yes.
Okay. Oh, Kakalo, you can stop sharing your chart.
I think, okay. There we go.
Yes. George, do you want, oh, you don't have the video. Okay. Camera, I mean.
Right. I apologize.
Okay. No problem.
So you've seen my chart?
Yes. Coriolis spores, right? Okay.
Yes. I'm back to the first chart.
Excellent. Go ahead.
Okay, I'm in Huntsville, Alabama, and we're having a storm here. So if I get knocked off, then you know why. But hopefully it's kind of quiet right now. So anyway, the first version of this particular presentation, I gave at the ISS R&D in 2023. And then last year, Dr. Prasad joined me in being co-presenter, and he's been helping quite a bit with the physics aspect of this, and I'm very thankful for the way he's been helping. So, before I get into this, I want to just share with you, I saw a video on YouTube the other day where it was about gravity, and so I was interested in it. I was watching it, and then at the end, the comment was made that, well, humans cannot be inside of a centrifuge in space because it'll make them dizzy. So I thought that was pretty interesting. And so this presentation attempts to get down, cut through all the hype and get down to the bare, what do we know? And sadly, the problem is that there's not a lot of summative data or empirical data that with humans for sure, because there's been no, like here, no documented large on orbit centrifuges capable of generating artificial gravity for humans. So the purpose is to explore the potential of using centrifugation to create artificial gravity in space environments to mitigate health risks and adapt terrestrial appliances for space use. And there's a couple other interesting investigations too. So the studies on Earth have been using the head down bed rest a lot and trying to mimic the microgravity effects. And the current ISS centrifuge facilities were not designed for large scale investigations involving conventional appliances or human subjects. The method here is to gain an understanding of gravity from the two relativistic frames of reference, one being the encapsulating inertial reference frame and the centrifuge's internal non-inertial relativistic reference frame. So initially, a design for a compact test article to incorporate common features of the larger centrifuge into the smaller centrifuge design to test out various investigations and conduct testing on ground drop towers, parabolic flights, wherever it may be useful. And then these test results can be used to validate simulations as well. So quantum gravimeters at key points within the centrifuge and on the outside of the centrifuge to be able to gather that sort of data and help validate the hypothesis that Einstein had. And that is that he imagined an observer in a large chest in a low gravity region of space, where if the chest accelerated upwards, any experiments performed inside of it would be equivalent to those in the gravitational field. So really, there's no magic going on here. It's just that if you're in a place where there's not much gravity and you're floating inside of a chest and the chest starts moving at the rate of gravity, the fall of gravity, then you, from an external observer, it's going to look like, and for all practical purposes, it will be like gravity. But if you were to take this chain, start swinging it, then the trajectory of the object inside would not be vertical similarly. So anyway, the orbital space station, for all practical purposes, is an inertial reference frame, but within a centrifuge, it is a relativistic non-inertial reference frame since it's rotating. So why use a centrifuge? These 5 basic areas of investigation have been identified. Health mitigation. So if astronauts were, say, in their sleep cycle inside of a centrifuge, or the whole time inside of a centrifuge, how would this mitigate the health issues that have been observed on long missions? For an appliance, if you take just a terrestrial appliance and then retrofit it for space use, that's never been done. That any of the research papers I've seen, and you would think that that would actually work the same as on Earth, but I'm sure there are some things that we won't predict. So as far as the space stations and probes, and looking at short radius centrifugation, I know the plans that have been spoken of earlier about VAST having a longer axis is not short radius, but then for short radius, there's not been sufficient investigation. So on the Coriolis effect, so the idea would be to build a habitat for rodents that's incorporating various design elements of the space station to see. For instance, there's a new company I saw, Titans. They have a spoke design space station, round spoke design. And so these various aspects that are called out in these papers I'm about to look at and show to you that have rules that you're supposed to go by to keep from experiencing Coriolis effects. So all of that could be tested out in more real environment. And then lastly, this centrifugation is an aid to sustaining reusable materials. And reusable materials may be better kept at 1G rather than low G. So there are some investigations out there. Dr. Peter Diamantis, he had an investigation in 1987 that showed within a centrifuge preserved T cell function. And that's severely hampered in microgravity. Then in 1977, they had, it was a high angular velocity of 53.5 RPM, but they did see an extended lifespan for the rodents. But these investigations, M31, 131, and 73 and 74 with the Skylab, it was not a centrifuge with this ocular counter rolling chair, which I'll show you a picture of that in a minute. There's no space motion sickness at all. And the Clement paper very recently from 2023 reanalyzed the data and found that all of that was within normal range. So this is a key, even though it's not a centrifuge, it's the closest thing that humans have been in orbit to compare with. And for appliances also, there's very little data. There's a 0G oven, which actually I think they did cook a cookie, but it took a long time to get it to the proper temperature and consistency. So the centrifuge would bring convection with the heating and also temperature gradients that you have in gravity. And so the very basic concept here is just to take like a basic pot and a hot plate, modify the lid, and have some hoses for ingress and egress, and see how well that does in microgravity. I don't have a mock-up for this, but like I said, if you were to take a habitat designed like with some of the design elements of space stations, and intentionally design into the habitat where you, in one case, you would break the rules defined by these papers that I'm about to show you. And in another case, have two different ones. Another case, you would obey those rules and then run the rodents through each case and see if there's any difference in their behavior. If the ones that are in the habitats that are designed to disobey those rules, are they getting disoriented, or do they have any adverse effects at all? So 3-meter centrifuge could be used for orbital human health mitigations, as well as off-world human health mitigations. Say if you're on the moon or Mars, and just get back to our baseline 1G, how could that help? Is it necessary, or those are the type of questions need to be asked. This is a picture from a NASA document done by Lockheed back in the 1990s. That's in Space Station Alpha days, but this is the type of centrifuge I think would be needed. And then the 1.25 meter centrifuge to evaluate appliances, do analysis here using rodents. And this is the ocular counter rotating chair using Skylab, and it would tilt up about 30 degrees this way and tilt back 30 degrees this way, and do that back and forth. And of course that is much more disruptive than if you're just to be going around and round. But even in this particular test in orbit, and one of the key things to understand is they waited 6 days. After 5 days, then they ran this test in orbit, because there are a lot of comparisons of this to say, the parabolic flights, but it takes about 5 days for humans to adapt to the microgravity. So that would be an invalid comparison, really. So if you're this man, you're walking on a rotating disc on Earth, then certainly you're going to lose your balance and fall. So if you don't have the pull of gravity here, then the real question is what effect would it have, really? Here's another severe or a boundary case where if someone is climbing a ladder and the conditions are correct and how the space station is designed, that person, when they get up here, it feels like they're moving in this direction. So these are the type of questions that really need to be asked or answered. And there have been rodents in rotating habitats in the station, but none of them tested these limits and were designed to gather data on whether the rodents would be disoriented. Basically, the testing is to determine if they had bone loss and that sort of thing. So so this basically reiterates, to build a smaller 1.25 meter model to do basic science investigations and using accelerometers to help validate these results. And possibly then develop analytical models to understand the nature of forces inside of these relativistic frames. Here's some equations, graph showing the angular velocity required versus the radius, and then the level of gravity. So this is the Coriolis acceleration here. These three papers are really good, and oop, there we go, and this one as well. But this is a good read too. It's not hard to read. It's not really that technical. So that's all I have.
Great, thank you so much, George.
Yeah.
Yeah, thank you so much, George. This is very interesting. So any question here in person or online? We are kind of delayed, so I think if no question, I have a quick, do you know this company called Spin Launch? It's here in Long Beach. They do this centrifugal, launch. It's another launch mechanism. Of course, it's but what I'm trying to say, they have some kind of hardware. You can do the centrifuge. Of course, it's a different purpose. I think they are too fast for doing on human, but I don't know that it is an existing system. But I'm not so sure that's human grade. It's mostly they try to
10,000 G.
Yeah, that's a cheap. But the people do build this kind of things, so I think it's an interesting idea, apply the physics, the coordinate from Cartesian to cylindrical coordinate system and to apply to the particle use. That's very interesting. Any question?
Okay, if not, thank you, George. We kind of behind schedule, so we cannot wait for people to ask. I think there's a question from. Oh, okay, that's not. All right. So thank you, George. We look for your next presentation with us. Thank you so much. Thank you. Yes. Good idea. So our next speaker is Mr. Joe Carroll. It's a very interesting presentation coming up. He actually can talk a bit longer, but he trimmed it to a little bit shorter for this mini conference, about 30 minutes, so people can enjoy this wonderful idea conversation. So thank you, Joe. While you are saying, we'll put your chart on the screen.
Okay.
So your chart is here. I need to.
Okay, and can you get this?
Yeah.
Great.
1 second, I'll give you this control. You can test it.
Great.
So this red one is a green laser. So this green laser for the red button. So this should move.
Okay.
Down arrow.
Yeah.
Move the chart, and the up is back.
Okay.
So I'll move back. Okay. So 1 second, let me share the screen for my folks, and we get started. Just 1 second.
Let's see, can we aim this a bit down because it's.
Oh, you? No, it's okay. People can see it. People can see it. Oh.
Yeah. Better. No, second. So good afternoon. I've talked a bit, providing a bit of teasers for what I'm going to talk about. And, Elon Musk wants to get us to Mars yesterday, okay? Occupy Mars. Bob Zubrin also wants to get us to Mars, slightly different schedule. And Jerry O'Neill, 50 years ago, proposed that maybe planets aren't the right place for an advanced civilization. And so he proposed spinning space stations. And you make them up out of recycled asteroids and moons, et cetera. The interesting thing about that is, Mars has all of its area is dry at the surface. Earth has a 3.3 times total area, but 70% of that is ocean. So Mars has the same land area as Earth does. Okay. Now, great, 2 places to go to live. If you go with spinning space stations, you can go to thousands of times more people and space. Okay. Freeman Dyson proposed the concept of habitats in space that are kind of like mosquitoes buzzing around the light. And they're so dense that they absorb most of the light. Okay, that's the limit of what we can do in this solar system. Okay. So the question is, do we go for broke with interplanetary, or do we try multiplanetary, or what? And I've been in aerospace for 44 years, and I find myself increasingly, my presentations and papers are questions, because there are questions that I think are important that we really, not only does nobody know, but we're not in a position yet to know. So let me talk about this. And the other thing is, this is actually from a space station view of Earth and just took a little slice of it. And I put that in the bottom of all my slides as a reminder to me that there's a lot yet to be done in low Earth orbit. There's a lot of stuff that can be done elsewhere, but my focus has been low Earth orbit. So let's see.
The down market, the down.
I don't know. Oh, okay. Okay, so what do these terms mean?
The red one is the laser.
Okay, let's see. I've got defective color vision, so which of these four things?
So this is the next chart.
Okay,
It's,
back.
Back, and
Yeah.
this is laser.
Okay, got it. Okay. So we've already covered these. Oops. Okay. There's an unexpected constraint on our future. To paraphrase Shakespeare, the fault is not in the stars, it's in ourselves. And the issue is, how much gravity do we need to have a good life? And the solar system is rather peculiar. We have 8 planets when you throw Pluto out, but 5 of them have nearly the same gravity. 2 more have the same gravity, Mars and Mercury. Okay, vastly different diameters and densities, but the same net effect, 0.38 G. And then there are 6 large moons, the 4 Galilean moons, Titan, and our moon, and they all have a reasonably small range of gravity levels. So basically, in this solar system, the gravity levels that are available are Earth, Moon, and Mars, and that covers 5 plus 2 plus 6, many places, okay? If you want to live somewhere that has more than Mars gravity, but doesn't have the complications of Earth-like gravity of Neptune, Saturn, Venus, and Uranus, there's nothing there, okay? So what it boils down to is, let's see. I went too far. Okay, two key takeaways. Our solar system has 13 bodies over a range of 0.09 G to 2 G, but all are clustered near Earth, Moon, and Mars gravity. And there are 4 other planets that have within 12% of Earth gravity, but one of them has 3 times the escape velocity of Earth. So if you go there, you're not coming back. The 2 more have more than twice the escape velocity of Earth, so you're not coming back either. And then Venus is a complicated situation to try to live in. You may be able to live in balloons in the sulfuric acid clouds at 53 kilometers above the surface, but there are only about 8 elements that you can get from the atmosphere, and the rest of them are down on the surface, and it's hard to get to them. So will the moon or Mars gravity provide enough for us? And what we have learned is there are a bunch of health issues. How many of you have read Packing for Mars by Mary Roach? It's a delightful study about what the complications are of trying to live on Mars. This is the key thing is that there are different sorts of problems with different parts of our body. And we found most of these problems only in 0G stays lasting 6 to 12 months. Planned moon stays are only less than 3 months. Okay, so we're not going to learn the sorts of things about our body in moon gravity anytime soon. And what will longer stays tell us? And will babies grow up normally? Okay, we know nothing about that. We're not in a position to know anything about that. Here's our current situation. That's microgravity. This is 1G, good health, high gravity. Oh, and Mars is closer to zero. Moon is a lot closer to zero. This is the problem. We have no idea what the responses our different immune systems are. And to make it more complicated, we probably will have different responses to different gravity levels for each of these 6 sorts of problems, okay? So to learn more about it, Packing for Mars, delightful read. Endurance is kind of a tough slog. And A City on Mars, which is a very critical approach, talking about the problems of actually trying to live on Mars. Now, ignoring novel health issues has sabotaged many large projects, and just 2, the Brooklyn Bridge, The Brooklyn Bridge was the first bridge that had caisson work at a deep enough level for the depressurization to go back to sea level air, caused deaths, and it screwed up the project and cost. And in the Panama Canal, there's a great book by David McCullough, The Path Between the Seas. It's 600 pages, and the first 240 is about the failed French effort. And it's an astonishing story. Even if you don't read anything more, once you start reading that story, you will want to complete it. There are so many curveballs in it that it's amazing. So will ignoring health issues delay human expansion beyond Earth? We simply don't know. So why should we try to test human health in low gravity in LEO, low Earth orbit, rather than the Moon or Mars? Well, costs. The costs to deliver cruise cargo to LEO are about 1/10 those to get to the Moon or Mars. Gravity tests in LEO need 1 facility, a spinning asymmetric facility, a dumbbell, and supply train to supplies. And on Mars, you need 2. You need separate moon base and Mars base and supply trains, okay? Another key issue is on-demand trips to and from LEO take hours, Moon days, and Mars on-demand trips, depending where you are on the cycle, it could be as short as 6 months, or if you miss that launch opportunity, maybe 30 months before you can get anything there, okay? There are other reasons to test low G human health. The same staff and equipment can have access to the people at both sides, so you can actually compare the effects of Mars gravity and Moon gravity on their health. The spinning facility, if you pay out a line and cut it, you can throw a capsule back to Earth without needing to handle rockets. And then if you do it in equatorial orbit, I'll show you that later, the ionizing radiation dose is far lower than on the Moon or Mars, or even than ISS. It's a factor of 5 lower dose, or a factor of 80% lower dose. Exposure to toxic materials on the Moon or Mars will complicate analyses. If you're on the Moon, you're going to end up, for months, you're going to end up with moon dust in your lungs, okay? And that will complicate the health analysis. So 2 challenges of artificial gravity, or AG. It's an orphan. It's not space exploration, it's not space science, and it's not microgravity science. Okay? When NASA does a study on artificial gravity, which every 10 years or so, it does a study that the results are, the only thing that's changed is that 7 years or 10 years since we did the last study. NASA has avoided artificial gravity since Gemini 7 crew survived 2 weeks in microgravity, and 2 weeks was longer than any planned Apollo mission. The longest was 12 days. And the fact that they were able to handle that, I don't know how well they worked together. I mean, it's like spending 2 weeks in the front seat of a VW, 2 guys, okay, except that it was not that roomy. I really think that the best human test, the best test of artificial gravity in humans was the astronauts that ran around a ring of computer boxes, about 20 feet in diameter. They ran around it and made their own artificial gravity by running, okay? They were in free fall until they started moving around. We can't test most artificial gravity effects properly on the ground. We need tests in orbit. There are a couple things you can learn from ground-based tests, but most of it you have to learn. And the reason is vertical axis rotating rooms, which is what we have done to make our guesses as to what spin rates would be acceptable. They cause consistent felt effects. If you put your arm out and you're spinning, you get a pull like this. Now, you do it a bunch of times and you eventually correct for it. You turn around, you have the same force, so you correct for it. If you're in artificial gravity, every time you turn around, the force changes direction, and so you can't adapt as well. Now, realistically, we are in artificial gravity right now. 1 turn per day with about 0.25% reduction in actual gravity due to the spin, okay? So you probably hadn't thought about that, but we can handle very small spins and not even notice them. But we really don't know how much we can tolerate. And for example, this guy is in a spinning room, and they spun up, and then they said, do this. And he went like this, or let's see, this way. And after a while, it was natural. It came like this. But then they brought it to a stop and asked him to swing his arm again, and he corrected in the other direction, okay? It would have been even worse had it been 10 RPM in the other direction, okay? And every time you turn around, that's the experience you get. So why use rotating dumbbells as the shape? Why not use the donut? Okay, von Braun wheel or donut. This has the lowest mass and volume, and all of that volume is concentrated where you want it to be, other than the 1 or 10% mass for the space in between. As you go from left to right, you get much more mass and volume. I mean, if you're doing a O'Neill colony, you do this. But if you're doing tests for artificial gravity, you do this because it allows you to have a large diameter with very low test mass. Okay. Now, you can do even better than this by having an asymmetrical dumbbell that has Mars gravity at one end and moon gravity at the other. And the nice thing, one of the other nice things about dumbbells is we don't know what radius we need. So dumbbells are the easiest to change. All you have to change is this length, okay? Now, I've got 4 slides coming up after these, and just this is a preview of ground tests that you can do that's relevant. Tests in LEO, first to find out what spin rate we can tolerate, and then Starship and Dragon to test Moon and Mars level gravity for months. And then devise a resort where the passenger, the customers flow through every week or 2, but the staff that stays there for a year or more. And that's how you get data that's useful, okay? Now, whether that's viable, I don't know, but I can't figure out any other way to learn these things that makes more sense than that, okay? I'm not saying it makes sense, but find something else that tells us important things other than that. And then when you do this, when you finish, you can figure out where you can live. And then we can go do that. Now, the first step is to test responses. In artificial gravity, if you walk with the spin, you get heavier. In fact, with the astronauts in Skylab, it wasn't even spinning, so you had no weight until they managed to get moving, okay? There's a facility at NASA Ames called the Vertical Motion Simulator. It has a 60-foot stroke up and down vertically, and I think 15 feet in the other direction and 8 feet in the other, in the third direction. But there are 4 or 5 interchangeable cabs, and the largest has this, it's basically this shaped room that's large enough that 2 people could walk around in an elliptical circle as the facility is doing this. And how far you stroke simulates different spin rates. And rather surprising, rather surprisingly, to simulate 10 RPM spin, you have to stroke 7.6 meters, which is 25 feet roughly, up or down, as you're walking around in 8.5 seconds, okay? That would be a big change. And that's, some people think that 10 RPM should be fine. I am skeptical, but this is a test we can find out, okay? But this tests only 1 G. It can't test responses in low gravity. And the effects are the same. If you're doing the test in 40% gravity, the effect seems 2.5 times larger because the effect is having the same effect, but gravity is only 40% as large. Oops. I don't know why. It's, well, it's stopped moving.
Let's see. Oh, yeah, I think it's Sherry. 1 second. It should be back now.
Okay. Yeah, okay, this is a sequence. This is a test done on Gemini 11. It was a spin test, but it was not done to test artificial gravity. It was a test to see how slowly 2 objects that were tethered together could spin and not run into each other, okay? And it went around at 40 degrees per minute, okay? Much slower than this. The rocking back and forth is actually oscillation of the end mass. But this test came after the Gemini 7 had gone 2 weeks in microgravity. NASA's interest is in past the station creeping, not on microgravity. So what I propose is to do a test with Dragon with the Falcon's second stage still attached. And then when you spin up, that gives you roughly a 4-meter difference between the crew position and the center of motion. Okay, that's the equivalent of an 8-meter diameter centrifuge, which is larger than anything anybody talked about, the last presenter talked about. Okay, then beyond that, you'll want to test. I mean, if you start doing things like this, you're going to also want to do this eventually. Okay, this is a more challenging thing, but it allows you to get any radius, spin radius you want. And so it allows you to get different combinations of spin rate and gravity. And I think that something like this could end up becoming a regular part on Crew Dragon missions. Okay, I put in a proposal that the program that the proposal opportunity that David Caponio mentioned earlier, I put in a proposal on doing these. Okay, step 3 is to do something much longer. And this is the size of the original user guide for Starship. It's no longer valid, but I sized it for that. And so you have 3 of these Starship modules and 2 Crew Dragons. And then you deploy a inflated tube and then inflate the whole length and then spin up. The same thing that you were doing with Crew Dragon. But now you've got enough supplies to live there for 6 months or 12 months and start to get real useful data, okay? For whatever length, for whatever length here that you decide is best based on the prior tests on Crew Dragon. Okay, step 4, that's where you expand this thing into a resort. And 3 modules here, or maybe 30 modules. It depends on how many customers you can find. Spin, center of gravity where you can dock, and a low G position. This position is as much smaller in proportion to as this is to this. Okay, so it's 1 step down from the moon gravity level. Now, key impacts of equatorial LEO. Okay, there are no launch sites truly at the equator within a half degree or 1 degree. There's the San Marco platform, Italian platform, and an oil derrick off Kenya. But that's, I think, at 2 degrees, 2.5 degrees. You really, for radiation protection, you want to be at least below 12 degrees. But for launch and inclination, for launch or reentry on any orbit, you really need to be less than 1 degree inclination, okay? And objects in equatorial LEO stay coplanar, and that makes it a lot easier to visit them. If something's 100 kilometers higher than you, it goes by you go by it, under it every 3 days, and you can get to it very easily. So this sort of facility could also host a free fall site, free fall laboratory. And by the way, since you're going to be having passengers fly up here regularly, if any personnel need to get to the other facility, it's a matter of days to get there, okay? To get onto here and then to take a Crew Dragon to visit the other place, okay? Disadvantages. Oh, and another advantage is you can assemble and test huge geo satellites in ELEO, okay? It's much, I think it's something like 400 or 800 meters per second delta V less than coming from Florida, okay? And it's not so much the change in Earth's spin, it's the fact that you don't have to get rid of that spin when you get up to geo. You don't have to get rid of that tilt. Disadvantages, you need new spaceports, okay? And another one is you can't see most of Earth directly from there. You're just going by the equator, the tropics. But my suspicion is that you're going to be able to get real-time, anywhere views on the internet in a couple more years, okay? So here's a view of two different views, right angle difference, of a Mars facility, the Mars Moon facility, and it's slowly turning here and here, and that's real time. Now, this is 1,000 times larger, and the orbit altitude is twice as high as it should be, but it shows you this sort of thing, this sort of dynamics that you would have. Now I'll speed it up, and now it's showing 80 times real speed. And one of the interesting things about this is that this is spinning in a plane, the spin axis goes close to the sun. It doesn't go up and down with the seasons, but by tilting the plane very slightly, you can get a torque that causes it to track around the sun each year so that it stays tracking close to the sun without any tracking of the solar arrays, okay? You can provide cheaper, larger solar arrays if you're in a low radiation environment and have this spin, okay? And here's the tilt that you need in order to get the facility to turn around as the Earth goes around the sun. Okay. A colleague of mine who's probably online did this, and I'm amazed at how useful it is for understanding what the orbit is going to be like. Now, the idea of going to Mars and putting people there and saying, okay, go for it. Realistically, facility waste, the stuff you throw away, has exactly the elements you need, not to expand the facility, but to sustain it. Recycling, you know, throwing something in a can is not recycling. That's 1% of the cycling that makes it a new beer can, okay? This is recycling to a Home Depot product, okay? Or doing it with Mars dirt to get to that. You need miracles. And mostly they're the same miracles, but I think you're going to need more miracles for this than for this, okay? Space settlers need to do their homework before they leave, okay? Useful recycling, useful waste recycling is hard, but skips ore handling. And I think settlers are going to reuse everything and then mine what they need to and import what they can't mine, okay? And economies are needed. This recycling everything is referred to as a circular economy, okay? We're going to do that, go that way eventually, very slowly on Earth, but it's what you have to start with to be viable in space if you only have new traffic every 2.5 years on Mars, okay? We need to do this now, and I suggest that we start doing it more on Earth and at that resort. You're going to have lots of stuff coming. You're going to start recycling it then. Okay. We can test crop automation on Earth and then in Elio. And keep in mind that low gravity will affect crops, their biomes, and cultivating procedures, and all the stuff needed. Farming is a challenging occupation, and if you don't know anything about it, you think it's simple. You know, you just throw the seeds and then pick it up later. No. Sustainability can cross-fertilize Earth and space farming. We will learn things in space that we didn't expect that will tell us something that we didn't expect to learn on Earth, and vice versa. And the final thing, in terms of satellite homework, is, you know, Elon makes a big deal of the importance of having the second stage be reusable and rapidly reflyable. I think that for each starship that goes beyond Earth orbit, there will probably be 10 of order 10 tanker loads. And tankers can be simpler vehicles, especially if they don't have to re-enter and land. And so it's quite possible that tankers may be more useful as reusable structures in orbit, if you design them for that, than bringing them back to Earth. You don't need TPS, you don't need fairings, you don't need propellant for landing. I think this is a part of the story in the long run. Okay, I have just about 30 references here, and for anybody that wants this presentation, I'm happy to send it to you, or Ken, or you. Yeah, okay. That's available, and most of them are things you can find online. And then conclusions. Your conclusions. Okay, I know mine. I'm curious about yours. Human health. Where should we start to test the human health in long-term low gravity? Leo or equatorial Leo, or the moon or Mars? Any suggestions?
I know the answer from Zubrin. Zubrin definitely goes directly to Mars.
Zubrin and Elon's,
yeah.
Yes.
Just go to Mars.
And that does have an advantage, that if that's not good enough health, you know that you don't have to go to the moon, because it's going to be a lot worse. Okay, that's the one argument that I know, other than, gee, it'd be fun, for going to Mars. Okay.
And I know for NASA, they want to do it space station test first.
Yeah. The second question is farming and recycling for a space settlement economy. Where should we test that? Start testing it at? On the ground, or ELEO, or the moon, or Mars? And keep in mind that stuff that you do on the ground is infinitely cheaper than stuff that you do in LEO, and that's 1/10 as expensive as what you do on the moon or Mars. Okay. So, as I mentioned earlier, robotic spacecraft are much better at doing space exploration than humans are. They get there faster, they stay longer, they bring more sensors, and you don't have to worry about losing the crew. Okay, the only advantage that I know of is that when the people come back, they bring back samples. But right now we have a problem, even with the robotic samples, that we don't know ways to bring back the samples we've collected in ways that are acceptable politically and diplomatically to avoid what is called backward contamination. We don't want anything to come back unless it's frozen and secured for science purposes, or unless it's cauterized beyond where any life form could be there. And you can't have anything in between, okay? That's the real problem with bringing stuff back from the moon, from Mars, okay? The moon, it wasn't a problem because there was no plausible argument for life forms on the moon. So I want you to think about these questions. I mentioned that my talks have lots of questions in them, and whoops. Where are we going to go? Okay, this is my take on a O'Neill colony where you expand it rather than, and live, half of the air of the volume in this is in areas that are levels where you could live. And instead of looking at all this open space, only half the space is open. And one of the interesting questions here is, where is the high rent district going to be? Is it going to be Earth, Mars, Moon, somewhere in between? Think about it, okay? One of the key things is you may go dancing here or here, but do your exercise here, okay? All it is an elevator ride that takes a minute or two. I think that artificial gravity does have that advantage over real gravity, that you can get any gravity level you want within a minute or two, okay? And that's something that we'll only know if that matters when we have a resort where people can do that, okay? So whether such a resort is feasible, I don't know, but I don't know any other way to learn this stuff that makes more sense than that. That's it. Any questions?
Just first, thank you. Yeah, any question online or here? Let's see which folks online. George, I think you want to say something. I saw you type in the chat. George, do you want to speak out?
Yes. Thank you for your presentation. This is a very in-depth presentation, and I gave the one prior. So yeah, mine is more focused on getting some basic research done that should have already been done before we start designing space stations. I mean, yours is a long radius design, but then I've seen companies that have space stations that have a short radius type of design, and on that they're advertising they're going to build that at some point. So, but yeah, I certainly appreciate your diligence here. This is, and there's some overlap in what I used to talk about the Gemini 11 spin test and previous presentations and that sort of thing too. But and I think it would be good to do these sort of tests. But I don't know if you've heard of a new company. It's called Titan Space. They're building a space plane.
No.
And they've got a space station on the drawing board too. But that might be worth looking at.
Yeah, I recall talking with somebody from Mojave Airport about the fact that he had a Mach 5 airplane and wanted a tether to get the other Mach 25. And they said, no, you get Mach 20 and I'll give you the last 5. Okay, and tethers have an advantage over rockets in that the shorter it is, the lower the delta V, the smaller the forces. And so the penalty for tethers goes quadratically with delta V, whereas with rockets, it's almost linear, okay? It goes exponential, but tethers go exponential in the square of the delta V. So what it boils down to is, for a short enough delta V, small enough delta V, tethers will win over rockets, but for a long enough delta V, the rockets will win. So tethers are great for catching something that's almost in orbit and throwing it down the reentry to save that propellant. But it's not good for giving you half the orbit velocity or more. That makes sense?
Yes.
I have a colleague, Pete Swan, who's very interested in space elevators. The problem is that if you have a strong enough material to do that, you could probably use that same material to make a single stage to escape pressure-fed vehicle. The tanks didn't weigh anything, so you can do it, okay? I'm skeptical. Yeah, the thing is, you can do useful things with tethers at 1 kilometer per second, even to near the limit of what existing fibers like Dyneema can do. And one of the things about Dyneema and Spectra is if you keep them white so that they stay cold in orbit, they can be 50% stronger and creep goes away. So you can do impressive things, but that only takes you about 2 kilometers a second. Okay, you need 8. Any other questions?
George, I see you post another comment here. Do you want to elaborate on that, about the radiation? Or
Yes, basically all I was saying is on your question number 1 there at the end, should we test it in ELEO or on the moon or Mars? And I said, well, humans may not survive the trip to Mars because of the radiation, but
yeah,
I think you need the due diligence in low Earth orbit in order to have a robust system design so you don't die on the way there.
Yeah, and equatorial Leo, Al Globus, a retired NASA person from NASA Ames, who also taught at community college, he was the one that proposed ELEO as the place for the first space settlement. And I asked him about where you would test, or what you would do to test the required diameter of that. And he says, your design, okay. ELEO is just made to order for frequent traffic, long-term stays with no radiation shielding. The only boring thing is that you don't get to see the rest of the Earth, okay? But again, cameras and the internet are going to solve that whenever the geospatial mapping agency stops being persnickety about using cameras in orbit.
So maybe some different ways of maybe trying to approach some of the science questions. So like one.
Some of the questions might be, could we learn something about the health effects of low gravity by sending tissue chips or mice to the moon and comparing that, like if we watch like degeneration over time, and how could that help?
Well, one of the unusual things about doing health tests long-term is you don't have anything that the crew is required to do 18 hours a day or 12 hours a day. So they can do a bunch of ISS-like things. They can reconstruct things that were built as Erectus sets. They can do all sorts of things to keep, they need to keep active, to not be bored and to stay in shape, because even in full gravity, if you're not active, you don't stay in shape. So one of the things that you need to do is to have useful things for them to do, and doing ISS-like tasks is one. Another is being the resort staff on a resort where you're busy taking care of the customers, okay? But what it is really secondary to the fact that you're getting really good health data on a large number of people who are staying there a year or longer, okay? And if it turns out, I mean, if there are people that will pay more for this research than the next passenger, there'll be more research done, okay? And the question of any of this makes sense, I don't know. And the question of what you have to do to make it make sense when it's not NASA subsidized is another key question. as I mentioned at the beginning of the panel, I think there is more uncertainty about the direction of our space program, civil and commercial space, than there ever has been. We went from, oh hell, the Russians launched a satellite, to Makeup and John Glenn, and then Apollo, and then after that, Shuttle. And by the way, NASA proposed to Nixon that we both do a shuttle and a space station. And he said, pick one. And so NASA picked the shuttle, but they turned it into an El Camino, which is a combination of a pickup truck and a car. It's not very good at each, but it's what you have to do. And that's if you want to do both. So not having a space station, NASA had to design a shuttle that had more room for people. And then we went from that to the ISS. Now we're at the end of ISS, and it's much less clear what should be the next thing. And in 2004, when the redirection of NASA to exploration, which then became labeled as the Moon, Mars, and Beyond, I thought it was fantasy and dropped out of AIAA and most of the meetings because I just thought it was sheer fantasy. And it's 21 years later, and we haven't done 10% of what we did in Apollo in 8 years. Okay. Apollo specified, my mentor, Jim Arnold at UCSD, said a rule for figuring out whether a chief of state means something in an address is whether he mentions the budget and says the number. If he doesn't, he's not serious. Okay. Apollo, Kennedy said, if you think you can do it for 25 billion, I will ask Congress for that, but don't expect to get anything more. That's the 25 billion. That's all you get. Okay. The current program has never had that focus. It's just been, well, let's just do it and kick the can. It's easier to kick the can 6 months or a year or 2 years or 4 years later. Okay. And I really hope that space station does not mostly splash in 2030. Okay. I think that there's enough going on that it'll be much more sensible to add pieces to the ISS and then figure out which pieces to throw away than it is to splash it and start over in a new way.
Yes, I believe that you should take nodes. If you're going to throw it in the ocean, might as well take nodes and put them together and test centrifuge concepts. You know, I don't know. That doesn't seem a wise use of what we have there.
There are a few NASA people that still remember Skylab, and Australians who will tell you to remember Skylab. Okay, it splashed in the Southern Ocean with parts of it raining down in Western Australia. That was 120 tons, which is small compared to the 420-ton space station, but large enough to be of concern. So even Falcon second stages, which were thought to demise completely until we found out that they didn't. Now Falcons leave a propellant margin reserve to deorbit after they kick their payload out, at least in NASA missions. I don't know about other missions. Any other? Yeah.
This doesn't really address your prompt about the testing, and I understand that's the scope of your presentation, but I did want to say, well, I wanted to ask if you've considered the implication that if we figure out that, if we understand the negative health effects of microgravity a bit better, that there might be a kind of like a biotech or pharmaceutical solutions to those?
We've been looking for that for 50 years, okay? Maybe it's just one turnaround the budget cycle. I don't know, but it started out as exercise. Then they realized, oh, well, I don't know the order in which the other two, but meds and diet. And it's a problem that gets longer, the more serious, and it affects more things when we stay longer. And when you send more people, you find things that you didn't notice in the first half dozen, okay? And so the fact that astronauts need a series of glasses of different diopters so that as their eyes change, they can still read. Okay, if you don't have the right glasses, some of them complain that they can't read anymore. Okay, so there may be a magic solution, but the magic solution may be artificial gravity. Okay. Another thing that some friends of mine argue for is spending part of your time in a centrifuge, but spending most of it in free fall. The problem is that when you're in that centrifuge, if you're just lying down, bed rest is the simulation of microgravity. So you've got to be standing or exercising or whatever while you're in that centrifuge. Okay. I suspect that people will get very quickly used to the idea of dancing and having sex in low gravity. I think that low gravity will end up being far more popular to short stay tourists than microgravity because, Buzz Aldrin said that it was easy to get used to the moon. It took a lot more effort to get used to microgravity. Okay. Any other comments, questions?
Yeah, just missed one thing. When you answered the question about the space elevator, you said
about what?
About the space elevator.
Yeah.
You just said that if we have like a strong enough material to build a space elevator, we can do something.
Yeah, that something is, there are many other things you can do, okay? And the problem with the space elevator is you can't do it at all until you can do the whole thing. There are other things you can do with existing tethers, and if they get twice as strong, you can do more delta V. But that is a driver for getting higher strength fibers. But the space elevator, you have to be able to get the whole thing. You can't do one that's, you can make a space elevator that goes between moon and that hangs from the moon partly into Earth's orbit because the delta V is small enough. It would be tremendously long. Okay, it would wrap around the Earth many times if it came down to Earth. But I haven't done these calculations. I actually did a study for BMDO in the 80s of a pressure-fed single-stage to orbit expendable vehicle. Okay, and I believe that can be done. I'm not sure it's the right way to compete with Starship, but it can be done. If you have a vastly stronger, more than 10 times stronger strength to weight ratio than cold spectra or Dyneema, then you might not just be able to make a space elevator, but you could make a rocket that could go single space to a state. Okay. And one of the interesting things about once you go beyond LEO, the further you go beyond LEO, the more valuable it is to keep the rocket where you're going, the rocket stage, and all its support equipment, life support, etc. I remember hearing Elon talk about dropping people off on Mars and then leaving. Well, at some point, somebody is going to have to certify that this vehicle is safe enough to fly back. And if it's somebody on Mars, they will never say that. because they will want to keep the stage there, okay, in case other hardware breaks and they need their hands on that, okay. So, and I think that's a rational choice, okay. So Elon eventually changed his mind and you know, stopped saying that they'll come back, okay. And even in LEO, if you're flying tankers, there's a lot of argument to be said that you can, you know, a tanker will have a volume that's a little bit larger than the propellant tank load. And you don't have all this area for an envelope or a fairing, okay? And when you put it up on the vehicle, there's no heavy 100-ton object sitting on top. So you can use balloon tanks, okay? You don't need struts. You don't need lots of extra structure. And something like that may be more useful. I mean, this is basically the wet workshop version of Skylab, okay? And even, I did a study in the early 80s of uses of aluminum from the shuttle external tank. You could use the shuttle tanks as tinker toys and build up huge structures, but what if you built as large a structure as you want and there are still more tanks coming up? Well, you can break it down and use the alloy. One of the calculations was that if you, I can't remember how many tanks it was, but I know that, well, if all the shuttle external tanks, the 135 of them, okay, except for the one damaged in Challenger, if you put those in orbit and turn them into a structural vehicle, it could be larger than the Aerospace Museum in Washington, D.C., and have a high enough strength to weight to be man-rated. Okay. Now, we don't have a need for that. But if we're going to do space settlements, we will want a need for that. And so some of the you know, the problem in LEO is there's no mineable stuff, but there's recyclable stuff. And if you're flying thousands of tons of Starlinks, well, maybe you should figure out a way to use the stages in orbit. The question of whether that makes sense depends partly on how much infrastructure you want to put up and how many flights go to that exact orbit. Because going to a different orbit, it's extremely difficult to change the orbit plane, extremely expensive in terms of fulfillment. But if you're launching stuff to ELEO, that stuff all stays in the same orbit, in the same orbit plane. And you can visit it. Oh, yes. Yeah. You can visit it and drag it to you know, you can put stuff in 600-kilometer orbit and then go get it later and bring it back when you're ready to recycle it into something else. Other questions?
I don't know if you knew, here at Marshall in Huntsville in, I believe, 2019, they did a study on using the fuel or the stages from the Artemis to put those in orbit and use those as a centrifuge, not to tumble end over end, but along its central axis, where it's similar to what you were talking about, where they did in Apollo, they went around the ring. Yeah.
Yeah, the Skylab crew. Yeah.
Yeah. So, and I think what they were saying is that is the largest element that's going to be put into orbit for the foreseeable future.
Well, for example, the step 2 slide that's up there now, the case of spinning test 1, where the stage is hard mounted to the back of the trunk. When you spin that up, you get about 4 meters separation between the crew standing on the ceiling with the seats tucked out of the way and the center of gravity of that assembly. And by the way, if you're standing inside a starship that's spinning around your long axis, and it's 9 meters in diameter, 4.5 meters, you go up a little bit, it's about 4 meters for your average CG. So the question of how to do that, you can test that. On that test one, what's the effect of any desired spin rate and gravity level at that spin radius? If you find that that's too much spin for the gravity you get, then you go to test 2 and make a longer radius, and then design a space station based on what's a long enough radius. When I first started I came up with the idea of a spinning dumbbell using external tanks in the mid-'80s. And then I dropped interest in it because I knew it wasn't going to happen. But in 2009, as I was getting over 62 years old, decided to write up these ideas. And the most frustrating thing about it was that I had no clue as to what was an acceptable radius. And finally, I showed a wide enough ranges that you should use 4 different structural types between the ends. And if it's short enough, it can be just modules end to end. If it's long enough, it needs to be a tube. If it's yet longer, one end can be a tube, and then the longer end would be a cable. And then if it's really long, it needs to be all cables. And we can't decide which one we need. Okay? This can tell us.
Any more questions? If not, thank you so much.
Okay.
Folks, you are welcome to continue the conversation, but officially we'll wrap up the session. This is the first time we do this, so we'll continue to do this, and the people have more chance to participate. And for people like Adrian and for the best space, we have more consistent opportunity for people to get engaged. Have experiment, on board a vehicle or vast space. We want to make it more routine, and also we want to make things like building in our daily life. That's why we're here trying to help everybody. And also microgravity, this actually, other than the space tourism, is another very great potential for fostering the space economy, and also the research and development, the material and the biopharmaceutical and those things. So it's great potential. Of course, another one is satellite starting, but I do think this there's many things that directly impact human life. I think this microgravity is certainly something very, very crucial. And Joe's proposal and Adrian and Nick and David company doing a great job. So thank you very much for participating with us, and the folks online, Dr. Prasad, George, also very good, sharing your insights. So thank you very much again. This is the first time we do it. Thank you very much, and we'll continue to learn and improve, and hopefully we'll make this very exciting and kind of your daily life, into this exciting field of microgravity. So thank you very much. Appreciate it. So we conclude the event now. We'll stop the recording, but you're welcome to continue the networking. The library room closed at 5:30, so we'll start to wrap up. We do have a little bit more coffee and donuts, cupcake left, so welcome to enjoy. Thank you. Thank you so much. Thank you.
Thank you for organizing.
Thank you. Oh, great pleasure. We'd love to do it.